Welcome to the Late Lab. It's really great to have you here. Before tonight's quiet little journey into the quantum world begins, let me know where in the world you're watching from. Maybe you're tucked away in bed. Maybe the room is dim and still. Maybe there's a cup of something warm nearby, slowly becoming more room temperature than intended. Wherever you are, I hope you're comfortable, settled, and ready to let your mind wander gently into one of the strangest foundations of reality. If you enjoy these calm explorations of science, space, matter, and the odd behavior of the universe when it thinks nobody is looking, a like and subscribe really helps this little channel keep going. And if you're already subscribed, thank you. Truly. Your support helps the Late Lab drift a little further through the night. Now, tonight's subject may sound tiny at first, because quantum physics deals with particles, atoms, probabilities, fields, and all the delicate machinery hidden far beneath ordinary experience. But the strange part is that this hidden world does not stay hidden. It shapes the chair beneath you, the screen in front of you, the light entering your eyes, the warmth in your hands, and even the chemistry quietly keeping you alive. So I'll try not to make quantum physics so interesting that it completely ruins your sleep. But if it does, at least you'll know that the world around you is not quite as solid, simple, or obvious as it politely pretends to be. So let's begin, shall we? How does quantum physics shape the world you know? Look around for a moment, and the world seems beautifully well behaved. A table sits where it is placed. A glass of water keeps its shape. A stone feels solid in the hand. The air moves invisibly through the room, soft enough to breathe, yet real enough to carry sound. Light spills from a lamp or a screen and somehow becomes colour, shape, distance, and meaning. Everything appears smooth, steady, and familiar, as if reality has agreed to follow a simple set of rules so nobody has to think too hard before bedtime. But beneath that calm surface, the world is not simple at all. Every ordinary object is made from atoms, and every atom is shaped by quantum physics. The table is not solid in the way it first appears. The water is not just a smooth liquid. The stone is not a single continuous lump of stuff. The human body is not merely warm flesh and bone. Each one is a vast arrangement of particles and fields, organized by rules that would seem deeply strange if they were visible in everyday life. Matter feels stable because electrons behave according to quantum principles. Light has color because photons carry energy in specific ways. Chemistry exists because atoms can share, exchange, and arrange electrons only in certain allowed patterns. Heat, electricity, magnetism, and the glow of a screen all depend on the same hidden foundations. Quantum physics is often introduced as if it belongs somewhere far away from normal life, sealed inside laboratories, particle accelerators, and equations that look as though someone spilled alphabet soup across a chalkboard. But that gives the wrong impression. Quantum physics is not an exotic decoration added to reality at very small scales. It is part of the reason reality has any familiar form at all. It is why atoms can be stable, why molecules can exist, why metals conduct electricity, why plants can absorb sunlight, why eyes can detect light, and why the device showing this video can quietly turn invisible electron behavior into images and sound. For most of human history, the world was explained through the language of classical physics. Isaac Newton described motion and gravity with astonishing success. His laws showed how falling apples, thrown stones, tides, planets, and comets could all be understood through clear mathematical principles. Newton's universe was not childish or crude. It was powerful, elegant, and so accurate in ordinary conditions that it still guides engineering, astronomy, and daily life. When a ball rolls across the floor, when a car turns a corner, or when a spacecraft is guided around the moon, Newton's ideas still do remarkable work. Then came James Clerk Maxwell, who showed that electricity and magnetism were not separate curiosities, but two parts of a deeper electromagnetic field. Maxwell's work revealed that light itself is an electromagnetic wave, travelling through space with a definite speed. That was one of the great unifications in science, a moment when nature seemed to become simpler and grander at the same time. The glow of a candle, the spark of lightning, the pull of a magnet, and the radio waves that later carried voices through the air all belonged to the same family. Classical physics was so successful that, by the late 19th century, some scientists thought the basic picture of the universe was nearly complete. There would be refinements, of course. There are always refinements. Nature has a habit of leaving small print at the bottom of the contract. But the broad structure seemed secure. Matter was made of particles, light was made of waves, forces pushed and pulled, and the universe ticked along like an immense, perfectly consistent machine. Then the small print began to glow. The problems appeared in places that seemed modest at first. Heated objects gave off light in a way classical physics could not properly explain. Atoms produced sharp lines of colour instead of a smooth rainbow. Light-striking metal could release electrons, but only when the light had the right kind of energy. Electrons inside atoms did not behave like tiny planets, orbiting a tiny sun. If they had followed the older rules exactly, atoms should have collapsed. Matter should not have been stable in the way matter plainly is. That is a rather important detail. A universe where atoms immediately collapse is not a universe with teacups, oceans, trees, planets, or anyone lying comfortably under a blanket wondering why physics has become so peculiar. Max Planck was one of the first to open the door. In 1900, while trying to understand the light emitted by hot objects, he introduced the idea that energy could be exchanged in discrete packets. These packets were later called quanta. At first, this was not presented as a full revolution in the meaning of reality. It was a careful solution to a specific problem, but it hinted at something enormous. Nature, at its deepest level, might not always change in smooth continuous amounts. Albert Einstein then took the idea further. In 1905, he explained the photoelectric effect by proposing that light itself could behave as individual packets of energy, now called photons. This was a startling move, because light had already been understood so beautifully as a wave, yet experiments showed that light sometimes behaved as if it arrived in indivisible pieces. Increase the brightness of the wrong kind of light, and electrons would still not be released from metal. Use light with enough energy per photon, and the electrons could escape. Nature was not asking how much light arrived in total. It was asking what each photon could carry. Niels Bohr used quantum ideas to explain why atoms had specific energy levels. Erwin Schrödinger developed a wave equation that described quantum systems in a completely new way. Werner Heisenberg introduced the uncertainty principle, showing that some pairs of physical properties cannot both be known with unlimited precision. Paul Dirac brought quantum mechanics together with special relativity, and helped reveal a deeper structure of particles and antimatter. These names can sound like statues in a scientific museum, but they were people trying to solve real puzzles forced on them by experiment. The universe was not behaving according to the comfortable script it had been given, and yet, strangely, the result of all this hidden weirdness is the ordinary world. Quantum physics does not make everyday reality dissolve into nonsense. It makes everyday reality possible. The atoms in a wooden table hold their structure because electrons occupy quantum states around nuclei. The table feels solid partly because electron clouds resist being pushed into the same arrangement, and because electromagnetic forces act between charged particles. The colour of a leaf depends on how molecules absorb and reflect certain wavelengths of light. The warmth of sunlight depends on photons released by processes rooted in nuclear and quantum behaviour. The chemistry inside the body depends on electrons forming bonds between atoms. Even the simple act of breathing relies on quantum-shaped molecules interacting in precise ways. This is why the title is not just poetic. Quantum physics really does shape the world you know. It shapes the firmness of the floor, the transparency of glass, the sparkle of metal, the softness of cloth, the taste of food, the signal inside a phone, and the light entering the eye. It does not replace the familiar world. It quietly supports it from underneath. The oddest part may be that this deeper layer rarely announces itself. A stone does not shimmer with probability. A cup of tea does not behave like a wave, although at a certain hour of the night it may feel spiritually close to one. A chair does not appear to be made from restless quantum fields. At human scales, enormous numbers of particles interact so constantly that the world settles into the smooth, stable patterns that classical physics describes so well. The quantum rules remain present, but their strangeness becomes averaged, hidden, and softened into ordinary experience. So the world feels solid, smooth, and predictable, because the deeper chaos is not really chaos at all. It is governed by precise rules, but those rules are not the ones human intuition evolved to notice. Human senses are built for fruit, weather, faces, footsteps, firelight, and the occasional suspicious noise downstairs. They are not built to directly perceive electron orbitals, photon energies, quantum fields, or probability amplitudes. Reality shows the mind a simplified version of itself, not because it is deceptive, but because survival rarely required seeing the fine print of the cosmos. Still, the fine print is there. Beneath every familiar surface is a hidden architecture of particles, fields, energy levels, and forces. Beneath the warmth of a hand is molecular motion. Beneath colour is the interaction between light and electrons. Beneath chemistry is the quantum arrangement of atoms. Beneath solidity is a world of mostly empty space held in stable form by rules that are invisible, exact, and quietly astonishing. Everyday reality is not separate from quantum physics. It is quantum physics, slowed down, crowded together, tangled with heat, shaped by vast numbers, and softened into the world that feels natural to touch, see, and live inside. The familiar world is the surface. Quantum physics is part of the reason the surface can exist at all. For a long time, it looked as though physics had found the main shape of reality. The world seemed to be made of matter moving through space, pushed and pulled by forces, warmed by heat, lit by waves of light, and governed by laws that could be written clearly enough to predict falling stones, swinging pendulums, tides, eclipses, cannonballs, steam engines, and planets. It was an astonishing achievement. Classical physics did not merely explain a few curious tricks of nature. It gave human beings a way to see the universe as orderly, measurable, and deeply connected. At the centre of that confidence stood Isaac Newton. In the late 17th century, Newton described motion with a clarity that changed science forever. His laws explained how objects keep moving unless something changes their motion, how force relates to acceleration, and how every action comes with an equal and opposite reaction. These ideas sound familiar now because they have become part of the mental furniture of the modern world, quietly sitting in the background like a very serious armchair. But at the time, they were revolutionary. They made the motion of everyday objects understandable in a precise and mathematical way. Newton's law of universal gravitation went even further. It showed that the same gravitational attraction pulling an apple toward Earth also helps guide the moon around Earth and planets around the sun. This was one of the great moments in human understanding. The heavens were no longer a separate, mysterious realm with different rules from the world beneath human feet. The sky and the ground belonged to the same physics. A falling object and an orbiting planet could be explained by one broad principle. That success made classical physics seem almost unstoppable. If a system's position, speed, mass, and forces were known, then its future could often be predicted with remarkable accuracy. The universe began to look like a great mechanical structure, not necessarily simple, but at least understandable in principle. A pendulum might swing, a planet might orbit, a wheel might turn, and behind it all there seemed to be dependable laws linking cause and effect. Nature was complicated, certainly, but not slippery. Then James Clerk Maxwell gave classical physics another triumph. In the 19th century, Maxwell developed a theory of electromagnetism that united electricity, magnetism, and light. Before Maxwell, electricity and magnetism had already revealed strange relationships. Electric currents could produce magnetic effects, and changing magnetic fields could produce electric currents. Maxwell gathered these discoveries into a deeper framework and showed that light itself is an electromagnetic wave. In one elegant sweep, sparks, magnets, radio waves, and visible light became different expressions of the same field. This was not a minor improvement. It was a grand unification. It meant that the glow of a lamp, the warmth of sunlight, the crackle of static, and the invisible signals later used for communication all belonged to a shared physical story. Classical physics now had Newton's mechanics for matter and motion, thermodynamics for heat and energy, and Maxwell's electromagnetism for light and fields. The universe seemed to be giving up its secrets rather politely, which is always suspicious in hindsight. By the late 19th century, many scientists believed the broad foundations were nearly complete. There were still technical problems to solve, of course. Measurements could be improved, equations could be refined, more details could be fitted into place. But the main structure looked secure. Matter consisted of particles. Light behaved as a wave. Heat was connected to the motion of many tiny constituents. Forces acted according to laws. Space and time provided the stage on which everything happened. And then, at the edges of this beautiful picture, experiments began producing results that did not fit. One problem came from black body radiation, the study of how ideal heated objects emit light. A warm object glows faintly in infrared light. A hotter object may glow red, then orange, then white as its temperature rises. Classical physics could describe parts of this behaviour, but when pushed to its full conclusion, it predicted an impossible result. It suggested that a heated object should emit far too much energy at shorter wavelengths. This failure became known as the ultraviolet catastrophe, which sounds like either a physics problem or a very dramatic band name, but it pointed to something serious. The old theory of light and heat was missing a crucial rule. Max Planck found a way through the problem in 1900. He proposed that energy could be emitted or absorbed only in discrete packets, not in any smooth amount whatsoever. These packets were later called quanta. Planck did not initially set out to overturn reality. He was trying to solve a stubborn calculation about glowing objects. But his solution introduced a new idea into physics. Energy at small scales might come in definite units. Nature might have a kind of graininess hidden beneath the apparent smoothness of heat and light. Another problem came from atoms themselves. By the early 20th century, experiments had shown that atoms contain negatively charged electrons and a tiny positively charged nucleus. But according to classical electromagnetism, an electron moving around a nucleus should radiate energy, lose speed, and spiral inward. In other words, atoms should collapse. That is awkward because atoms very obviously do not collapse. They build rocks, oceans, atmospheres, books, bones, stars, and the occasional biscuit crumb that somehow survives for weeks between sofa cushions. Atomic stability was not a small loose end. It was a direct challenge to the classical picture. If matter could not be explained, then the world people touched every day had become evidence against the old theory. The problem was not that classical physics was useless. It remained extraordinarily useful. The problem was that it could not explain why matter had the stable structure it plainly had. Light created another crack. In the photoelectric effect, light shining on a metal surface can knock electrons out of that surface. Classical wave theory suggested that brighter light should eventually provide enough energy to release electrons, regardless of colour. But experiments showed something different. If the light had too low a frequency, no electrons were released, even if the light was bright. If the light had a high enough frequency, electrons could be released almost immediately, even if the light was faint. Albert Einstein explained this in 1905 by treating light as packets of energy, now called photons. Each photon carried an amount of energy connected to its frequency. A single photon either had enough energy to release an electron or it did not. Brightness increased the number of photons, but it could not make each individual photon more powerful. This was a remarkable idea because light had already been so successfully understood as a wave through Maxwell's theory. Now, in certain experiments, light had to be treated as particle-like as well. So classical physics did not fail because it was foolish. It failed because it was brilliantly successful in one domain and incomplete in another. It worked beautifully for planets, bridges, falling objects, engines, waves, and many everyday motions. It still does. But when physicists looked closely at heated objects, atoms, electrons, and light, nature refused to behave like a smooth mechanical machine. Quantum physics emerged because experiments demanded it. Scientists did not invent it to make the universe sound mysterious. They were not sitting around thinking that physics needed more drama, perhaps with a little probability sprinkled on top for flavour. They followed evidence that kept pointing away from the old assumptions. Energy came in packets. Atoms had allowed states. Light behaved as both wave and photon. Electrons did not follow simple classical paths inside atoms. Matter itself seemed to require deeper rules. The important lesson is that classical physics was not thrown away. It became part of a larger picture. At human scales, where objects are large, speeds are ordinary, and quantum details are usually averaged out, classical physics remains one of the most useful descriptions ever created. It explains the motion of cars, planets, falling rain, and swaying trees with extraordinary power. But beneath that visible layer, the stability and behaviour of matter depend on quantum principles. The familiar world did not stop obeying Newton and Maxwell. It simply turned out that Newton and Maxwell were describing the upper surface of a deeper reality. Classical physics explained how the world moves once it already exists in a stable form. Quantum physics began to explain why that stable form exists at all. The first real doorway into quantum physics did not open with a dramatic image of particles flickering in and out of existence, or with someone staring thoughtfully at a mysterious glowing machine. It opened through something much more ordinary. Heat. Heat seems familiar. A stove warms a room, a candle glows, metal in a forge turns dull red, then brighter orange, then almost white if it becomes hot enough. Stars shine because they are intensely hot, and their colours carry information about their temperatures. A cooler red star gives off a different kind of light from a hotter blue-white star. Even the human body gives off infrared radiation, invisible to the eye but detectable with thermal cameras. In a very quiet way, every warm object is speaking in light. This glow from warm objects is called thermal radiation. A perfect version of such an object, one that absorbs and emits radiation as efficiently as possible, is called a black body. The name sounds slightly ominous, as if it belongs in a locked drawer in a Gothic laboratory, but the idea is simple enough. A black body is an ideal object used in physics to understand how heat and light are connected. It does not reflect light in the usual way. Instead, its glow depends on its temperature. By the late 19th century, physicists were trying to explain blackbody radiation using the tools of classical physics. The challenge was to predict exactly how much light a heated object should emit at different wavelengths. Some of the predictions worked in certain ranges, but when the classical theory was pushed towards shorter wavelengths, it failed badly. It predicted that a hot object should emit an impossible amount of high-frequency radiation. This failure became known as the ultraviolet catastrophe, which does have the unfair advantage of sounding like a very energetic disaster at a science-themed nightclub. The problem was not that heated objects actually behaved catastrophically. The problem was that the classical theory did. Real objects glowed in a smooth and measurable way. Furnaces, stars, and hot metal were not pouring out infinite energy. Nature was behaving sensibly. The equations were the ones having a difficult evening. Max Planck approached this problem with great care. In 1900, he found a formula that matched the observed glow of heated objects. To make the formula work, he proposed that energy was not exchanged in any amount whatsoever. Instead, energy was absorbed or emitted in tiny discrete packets. These packets became known as quanta. This was an astonishing step, but Planck did not initially present it as a complete new picture of reality. He was not announcing that the universe was secretly built from probabilities, wave functions, and all the later strangeness that would make quantum physics famous. He was solving a very specific problem about how heated objects emit light. The quantum idea began almost as a mathematical necessity, a way of making the numbers agree with experiment. Sometimes revolutions do not arrive wearing a cape. Sometimes they arrive as a stubborn correction factor. The key scale in Planck's work is now called the Planck constant. It is one of the fundamental constants of nature, and it sets the size of quantum effects. The Planck constant is extremely small compared with the energies and actions involved in ordinary human life. That is why people do not notice quantum jumps while making toast, walking across a room, or trying to find the end of a roll of tape. At everyday scales, quantum effects are usually hidden beneath huge numbers of particles and interactions. But at the scale of atoms, electrons, and photons, the Planck constant is not a detail. It is the quiet ruler by which nature measures what can and cannot happen. The defining idea is quantization. Quantization means that certain physical quantities, such as energy in specific systems, can come only in allowed amounts. They are not always free to vary smoothly. This is very different from ordinary experience. A person can pour a little more water into a glass, then a little more, and then a little more again. A dimmer switch seems to raise or lower brightness smoothly. A car can speed up gradually. Classical intuition expects nature to slide between values without interruption. But atoms and molecules do not always behave that way. Their electrons can occupy only certain energy levels. When an atom absorbs energy, it can move from one allowed level to another. When it releases energy, it can emit a photon with a specific amount of energy. Because photon energy is connected to colour, atoms often absorb and emit light at particular colours rather than across one completely continuous smear. This is why atomic spectra are so important. When light from an element is spread out, it can reveal bright or dark lines at specific colours. Those lines are like fingerprints of the atom. Hydrogen has its own pattern. Sodium has its own pattern. Neon, mercury, oxygen, and iron each have their own patterns too. The colours are not random. They come from electrons shifting between quantized energy levels. This matters far beyond the laboratory. The same principle helps astronomers identify elements in distant stars. By studying the pattern of light from a star, scientists can tell what kinds of atoms are present, even though the star may be unimaginably far away. The universe, rather helpfully, labels its ingredients in colour. It does not include a friendly handwritten note, but one takes what one can get. Quantized energy also appears in ordinary technology. Light bulbs glow because electrical energy is transformed into light and heat. Lasers depend on carefully controlled quantum transitions that produce light with a precise wavelength and a highly organized structure. Glowing screens use materials whose electrons release photons in specific ways, turning quantum behavior into images, colors, and late-night scrolling that absolutely was meant to last only 5 minutes. Thermal cameras detect infrared radiation emitted by warm objects. Even the colors produced by atoms and molecules, from streetlights to fireworks to glowing signs, depend on quantized energy. So the discovery that energy comes in packets was not just a strange technical fix. It was the first clear sign that the smooth surface of reality hides a deeper grain. The warmth of a stove, the color of a star, the glow of metal, and the light from a screen all point back to the same unsettling idea. Nature does not always trade energy in a continuous flow. At its smaller scales, it often counts. And from that quiet act of counting, quantum physics began. light is one of the most familiar things in the world and one of the hardest to describe honestly. It pours through windows, warms skin, reflects from water, paints the sky blue, turns leaves green, and lets a face appear on a screen in the middle of the night. It feels so ordinary that it almost disappears into the background of a life. But when physicists began asking what light actually is, the answer became stranger than any simple picture could hold. For a long time, light had been understood as a wave. James Clerk Maxwell's theory of electromagnetism showed that light is an electromagnetic wave, made from linked electric and magnetic fields travelling through space. This was a magnificent explanation. It described visible light, radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays as members of one broad family. They differed mainly in wavelength and frequency, which is why red light, blue light, radio signals, and X-rays can all be understood as different expressions of the same electromagnetic field. The wave nature of light is not just an abstract idea. It can be seen through interference and diffraction. When waves overlap, they can strengthen each other or cancel each other out. Ripples on a pond do this. Sound waves do it too. Light behaves in a similar way. In interference experiments, light can form bands of brightness and darkness, as if two sets of waves are arriving together and either helping or hindering one another. In diffraction, light spreads as it passes through a narrow opening or around an edge. These behaviours make excellent sense if light is a wave. Colour also fits naturally into this wave picture. Different colours of visible light correspond to different wavelengths. Red light has a longer wavelength than blue light. The colours seen in a rainbow appear because sunlight is separated into its different wavelengths. So far, light seems very wave-like indeed. It moves, spreads, bends, overlaps and forms patterns. It behaves almost politely, which in physics is usually a warning that something more awkward is waiting nearby. That awkwardness appeared in the photoelectric effect. The photoelectric effect happens when light shines on a material, often a metal, and causes electrons to be released from its surface. Classical wave theory suggested a fairly simple expectation. If light is a wave carrying energy, then making the light brighter should provide more energy. So even light of the wrong colour ought eventually to release electrons if it is intense enough. Give the surface enough light, wait long enough, and surely the electrons should be shaken loose. But that is not what experiments showed. If the light had too low a frequency, no electrons were released, no matter how bright the light became. The surface could be flooded with light, and still nothing happened. But if the light had a high enough frequency, electrons could be released almost immediately, even when the light was faint. Brightness mattered, but only after the right threshold had been crossed. The colour, or more precisely the frequency, was the deciding factor. Albert Einstein explained this in 1905 by taking Max Planck's quantum idea seriously. He proposed that light can behave as individual packets of energy. These packets are called photons. Each photon carries an amount of energy linked to the frequency of the light. A photon of red light carries less energy than a photon of blue or ultraviolet light. If a single photon does not carry enough energy to free an electron from the material, then adding more low-energy photons will not solve the problem in the same way. It is like trying to buy one expensive item with coins that are not accepted individually. Having a pocket full of them may be emotionally reassuring, but the machine still refuses to cooperate. This was a profound shift. Light was not only a smooth electromagnetic wave. In certain situations, it behaved as though its energy arrived in individual pieces. The photon became one of the central ideas of quantum physics. It showed that light could not be forced into the old categories of wave or particle, as those words had been understood in classical physics. The photon is not simply a tiny glowing pellet flying through space. That image can be useful for a moment, but it becomes misleading if taken too literally. Light is described by quantum rules. In some experiments, its wave nature is unmistakable. In others, its particle-like exchange of energy is essential. The same light can produce interference patterns and also arrive as discrete detections. It is not changing costumes to confuse scientists, although one could forgive that interpretation after a long afternoon in the laboratory. It is revealing that the categories built from everyday experience are not deep enough. This strange double nature is not locked away in old experiments. Photons shape modern life constantly. Solar panels work because photons from sunlight transfer energy to electrons inside semiconductor materials, helping generate electric current. Digital cameras detect photons using light-sensitive electronic sensors, turning patterns of light into images. Automatic doors, light meters, barcode scanners, remote controls, fiber optic cables, night vision equipment, and many forms of medical imaging all depend on the controlled interaction between photons and matter. Every photograph is a record of photons arriving. Every screen is a carefully engineered flood of photons sent toward the eye. Every light sensor is a small agreement between quantum physics and practical design. The world of modern imaging, communication, and electronic vision depends on the fact that light can deliver energy in individual quantum packets, and yet the wave picture remains true as well. Light still diffracts, it still interferes, it still has wavelength, frequency, and colour. Maxwell's electromagnetic theory was not discarded. It became part of a deeper understanding. Quantum physics did not simply declare that light was a particle instead of a wave. It revealed that light is something more subtle than either classical picture. That is the central lesson. At the quantum level, nature does not always match the categories that human beings built from familiar objects. A wave in water spreads through a surface. A particle of dust sits in one place and travels along a path. Light does not behave exactly like either one. It follows quantum rules, and those rules can produce wave-like patterns or particle-like exchanges depending on how light is measured and how it interacts. This idea opened an even stranger door. If light, once thought to be purely a wave, could behave in particle-like ways, perhaps matter, once thought to be made of definite particles, could show wave-like behavior too. The solid world had already begun to look less simple. Now even the boundary between light and matter was beginning to soften. The universe was not abandoning order. It was asking for a deeper kind of order, one that could hold waves and particles inside the same quiet truth. Once light had begun behaving like both a wave and a particle, physics had a choice. It could treat this as a strange exception, a special rule for light alone, and hope the rest of reality remained more sensible. Or it could follow the idea further and ask a more unsettling question. If light, which had long been understood as a wave, could also behave in particle-like ways, could matter, long understood as particles, also behave in wave-like ways? That question was taken seriously by Louis de Broglie in the early 20th century. He proposed that matter itself has wave-like properties. Electrons, protons, atoms, and even larger objects would have an associated wavelength. This did not mean that an electron was secretly a tiny water ripple, or that a stone was about to slosh gently through the room like an unusually committed puddle. It meant that the behaviour of matter at small scales could not be fully described by the old picture of solid little objects moving along definite paths. De Broglie's proposal was bold because electrons had seemed particle-like in many ways. They carried electric charge. They could be detected in specific places. They could be knocked out of metals by light in the photoelectric effect. They were part of atoms and electrical currents. But quantum physics had already shown that familiar categories could become unreliable when pushed too deeply. Light was not just a wave or just a particle. Perhaps matter was not just a particle either. The crucial idea was that every moving particle has a wavelength associated with it. For tiny particles such as electrons, that wavelength can be large enough, relative to atomic structures, to produce measurable effects. For ordinary objects, the wavelength is unbelievably tiny. A person walking across a room has a matter wavelength, but it is so small compared with the size of the person, the room, the floor, and everything else involved that it has no visible effect. This is why people do not diffract through doorways. Cups do not spread into wave patterns when placed on tables. Chairs do not interfere with themselves, although some chairs do seem personally committed to being in the way. And sandwiches, despite many mysteries, remain disappointingly classical. The wave nature of matter had to be tested. One of the most important confirmations came from electron diffraction. Diffraction is a wave behavior. When waves pass through openings or around obstacles, they can spread out and form patterns. Light can do this. Water waves can do this. If electrons could also produce diffraction patterns, then de Broglie's idea would have strong experimental support. In 1927, Clinton Davison and Lester Germer observed electron diffraction while studying electrons scattering from a nickel crystal. The electrons produced patterns that matched wave-like behavior. Around the same period, George Paget Thomson also demonstrated electron diffraction using thin metal foils. These experiments were remarkable because they showed that electrons, which could be detected as particles, also behave like waves when interacting with the regular structure of crystals. Nature was no longer simply hinting, it was quietly underlining the point. This does not mean that matter waves are ordinary waves in a material substance. A water wave is a disturbance moving through water. A sound wave is a disturbance moving through air or another medium. A matter wave is different. In quantum mechanics, it is connected to the wave function, a mathematical description that gives information about the probabilities of possible measurement outcomes. The wave function can spread out, overlap, interfere, and evolve according to quantum rules, but it is not a little physical ripple in the everyday sense. It is stranger than that, and also more precise. This is where the language becomes delicate. An electron is not simply a tiny ball with a wave wrapped around it, nor is it merely a vague cloud with no physical meaning. When measured in certain ways, it can be detected at a particular location. When allowed to evolve and interact without being pinned down, it can show wave-like behavior. The electron is described by quantum mechanics, and the words wave and particle are useful clues rather than perfect labels. They are borrowed from the large world, where waves and particles are easier to imagine. At the quantum scale, the borrowed words begin to creak a little. Matter waves are not just philosophical curiosities, they are directly useful. Electron microscopes use the wave nature of electrons to see structures much smaller than visible light can resolve. Ordinary light microscopes are limited by the wavelength of visible light. If the details being examined are much smaller than that wavelength, they cannot be clearly distinguished. Electrons can have much shorter wavelengths than visible light when accelerated in controlled ways, allowing electron microscopes to image viruses, cell structures, materials, crystals, and nanoscale surfaces in extraordinary detail. This is one of the beautiful turns in the story. The same strange wave behavior that once unsettled the meaning of matter became a practical tool for looking more deeply into matter itself. Electron microscopy allows scientists to examine the hidden architecture of cells, metals, semiconductors, proteins, and microscopic structures that shape medicine, engineering, biology, and technology. Quantum behavior is not merely something to be explained. It is something the modern world uses. The wave nature of electrons also became essential for understanding atoms. In older pictures, electrons were sometimes imagined as tiny planets orbiting the nucleus. But that picture could not properly explain why atoms are stable, why electrons occupy particular energy levels, or why elements produce specific spectral lines. Matter waves offered a deeper route. Electrons and atoms could be described as standing wave-like patterns with only certain arrangements allowed. These allowed patterns are connected to the quantist energy levels that give atoms their structure. This matters enormously. Atomic structure is the basis of chemistry. Chemistry is the basis of molecules, minerals, water, air, biology, medicine, food, and the materials used in technology. Chemical bonding depends on how electrons are arranged and shared between atoms. Those arrangements cannot be understood properly without quantum mechanics. The wave nature of electrons is part of why atoms can form stable patterns instead of collapsing into confusion. So de Broglie's matter waves helped change the meaning of matter. Matter was no longer just a collection of tiny hard particles. It had quantum behavior described through wavelengths, wave functions, probabilities, interference, and allowed states. The familiar solidity of the world did not vanish, but its explanation became more subtle. Beneath the stillness of a stone or the smoothness of a glass of water, electrons obey rules that have more in common with waves than ordinary intuition would ever expect. The strange behavior of electrons is not a side note in physics. It is one of the reasons the world has atoms, chemistry, materials, and structure. The particles beneath reality are not little pieces of clockwork. They are quantum objects, and their wave-like nature is one of the quiet rules that lets the ordinary world hold together. One of the strangest facts about the world is that it manages to stay here. That sounds almost too obvious to notice. Tables remain tables, stones remain stones, water stays made of water. A hand does not suddenly sink through a wall. The atoms in the air do not collapse into dense little sparks. Matter holds itself in patterns, and because those patterns hold, there can be chemistry, biology, planets, oceans, books, trees, and the small, everyday miracle of a mug surviving on a desk for longer than anyone expected. But under older classical physics, atoms presented a serious problem. They should not have been stable. The puzzle became sharp after Ernest Rutherford's work on atomic structure. In the early 20th century, Rutherford and his colleagues studied how tiny, positively charged alpha particles scattered when fired at thin gold foil. Most passed through with little change, but some bounced back at large angles. Rutherford realized that atoms could not be soft, spread out blobs of positive charge as earlier models suggested. Instead, most of the atom's mass and positive charge had to be concentrated in a tiny central nucleus. This was a major discovery. It revealed that the atom was mostly empty space, with a small dense nucleus at the centre, and negatively charged electrons somewhere around it. The nucleus was incredibly small compared with the atom as a whole. If an atom were expanded to the size of a large stadium, the nucleus would be more like a tiny object near the middle, while the electrons would belong to the much wider region around it. Matter, which feels so satisfyingly solid, turned out to be built from structures that are mostly space. The Rutherford atom was powerful, but it created an immediate difficulty. If negatively charged electrons were moving around a positively charged nucleus, they should have behaved somewhat like charged particles in orbit. According to classical electromagnetic theory, an accelerating electric charge should radiate energy. An electron curving around a nucleus would be accelerating, because its direction of motion would be constantly changing. So it should give off radiation, lose energy, spiral inward, and crash into the nucleus. In other words, classical physics seemed to predict that atoms should destroy themselves almost instantly. This is not a small inconvenience. If atoms collapsed, there would be no stable elements, no molecules, no chemistry, no cells, no rocks, no air, no oceans, no cozy late-night science videos, and certainly no one available to complain that atoms had handled the situation poorly. The stability of matter was not an optional detail. It was the foundation of the visible world. Niels Bohr offered one of the first quantum solutions. In 1913, Bohr proposed that electrons in atoms could occupy only certain allowed energy levels. They could not simply spiral downward through every possible path. Instead, electrons could remain in stable states without radiating energy, and they could jump between these states by absorbing or emitting specific amounts of energy. This helped explain why atoms produce particular spectral lines, especially the hydrogen atom, whose light appears at distinct colours rather than as a continuous blur. Bohr's model is often drawn like a tiny solar system, with electrons circling the nucleus in neat paths. It is a helpful historical image, but it is not the modern picture. Electrons are not little planets orbiting a miniature sun. The Bohr model captured something important about fixed energy levels, but it still carried too much classical imagery. The deeper explanation required quantum mechanics. Erwin Schrödinger provided a major step forward with his wave equation. Schrödinger's equation described how the quantum state of a system changes over time. For electrons in atoms, it allowed physicists to understand atomic structure through wave-like patterns rather than simple circular orbits. Only certain stable patterns were allowed, rather like how a vibrating string can support certain standing waves. The electron in an atom is not best pictured as a bead moving around a track. It is described by a wave function, and the allowed forms of that wave function correspond to possible energy states. This is where the idea of orbitals becomes essential. An electron orbital is not a path. It is a region of probability, a description of where an electron is likely to be found if measured. Some orbitals are roughly spherical. Others have dumbbell shapes or more complex structures. These shapes are not decorative scientific artwork. They come from the mathematics of quantum mechanics and determine how atoms bond, how molecules form, and why elements behave differently from one another. The important point is that electrons in atoms occupy quantum states. They are not endlessly losing energy in the classical way because their behavior is governed by quantist energy levels and wave-like rules. The atom is stable not because the electron has found a clever classical orbit, but because quantum mechanics allows certain standing wave-like states that do not simply collapse into the nucleus. There is also a deeper balance involved. Confining an electron to an extremely tiny region near the nucleus would make its position more definite, but quantum mechanics links such confinement with greater uncertainty and momentum. The uncertainty principle, introduced by Werner Heisenberg, helps explain why an electron cannot simply settle motionless inside the nucleus, in the ordinary atomic case. The atom's stability comes from quantum rules about energy, wave functions, allowed states, and uncertainty, not from a little electron carefully steering itself around disaster. This hidden stability shapes everything familiar. The carbon atoms in the body, the oxygen in the air, the silicon in computer chips, the iron in blood, the calcium in bones, and the hydrogen in water all depend on atoms having reliable structures. Chemical bonds form because electrons occupy quantum states around atomic nuclei. Molecules hold together because those electron arrangements can be shared, shifted, and organized in specific ways. Biology then builds on chemistry. Chemistry builds on atomic structure, and atomic structure builds on quantum mechanics. Solid objects are solid only because atoms and their electrons behave in stable, rule-governed ways. Materials have strength, flexibility, transparency, color, and conductivity because of how electrons arrange themselves in atoms and solids. A sheet of glass, a steel bridge, a leaf, a human cell, and a glowing screen all depend on the same quiet fact. Atoms do not collapse, so the stability of the world is not something classical physics could fully explain. Classical physics gave magnificent account of motion, forces, gravity, and electromagnetism at human scales, but the atom demanded new rules. It demanded fixed energy levels, wave functions, orbitals, and quantum states. The familiar world feels steady because its smallest structures are not obeying the old picture of tiny planets circling tiny suns. They are obeying stranger and deeper rules. Atoms hold together because electrons are quantum objects, and the allowed patterns of their behavior give matter its endurance. Every object nearby is a kind of quiet victory over collapse. The table, the wall, the air, the body, and the earth itself are all made from atoms that classical physics alone could not keep alive. The reason they remain, calm and ordinary, is that beneath them, quantum physics is doing the work. Even after quantum physics explained why atoms do not simply collapse, another quiet mystery remained. Matter was stable, but it was also structured. Electrons did not all crowd into the lowest possible state around an atomic nucleus. Atoms had layers, elements had distinct personalities, hydrogen behaved differently from helium, carbon behaved differently from oxygen, Sodium, chlorine, iron, gold, neon, and uranium each had their own chemical character, their own patterns of bonding, and their own place in the great arrangement known as the periodic table. The reason for this structure comes from one of the most important rules in quantum physics, the Pauli exclusion principle. Wolfgang Pauli introduced this principle in 1925 while trying to understand the organization of electrons in atoms. The rule states that certain particles, known as fermions, cannot occupy exactly the same quantum state within the same quantum system. Electrons are fermions, so are protons and neutrons. This means electrons cannot simply pile into one identical state around a nucleus, all sitting in the same lowest energy arrangement like tired commuters squeezing onto the same train seat. Each electron in an atom must have its own allowed quantum state. These states are defined by properties such as energy, angular momentum, magnetic behavior, and spin. The details become mathematical very quickly, but the high-level idea is beautifully simple. Electrons have a strict rule about sharing. They are not sociable in the way photons can be. Photons, which are bosons, can occupy the same quantum state in huge numbers. That is part of what makes lasers possible. Electrons refuse that kind of crowding. This refusal gives atoms their layered structure. As more electrons are added around a nucleus, they must occupy different available states. The lowest energy states fill first, then higher ones become occupied. This creates shells and subshells, a structured arrangement of electrons around the nucleus. The old image of electrons orbiting like planets is not accurate, but the idea of layers remains useful when understood through quantum states and orbitals. This is one of the reasons the periodic table has its shape. The periodic table is not just a clever filing cabinet for elements, although it is an exceptionally good one. Its repeating patterns come from the way electrons fill available quantum states. Elements in the same group often have similar chemical behavior because they have similar arrangements of outer electrons. Those outer electrons are especially important because they are most involved in chemical bonding. Hydrogen has one electron and behaves in a certain way. Helium has two electrons and forms a very stable arrangement. Lithium begins a new outer shell and behaves very differently. Carbon, with its electron structure, can form 4 strong covalent bonds and become central to organic chemistry and life. Neon has a filled outer shell, making it chemically unreactive under ordinary conditions. The personalities of the elements, from highly reactive sodium to noble quiet neon, are built from electron structure. An electron structure depends on the Pauli exclusion principle. Without this rule, chemistry would not have its familiar richness. Electrons would collapse into fewer states, atoms would lose their layered architecture, and the periodic table would not have the same repeating logic. There would be no ordinary chemical world of water, salt, oxygen, carbon compounds, minerals, proteins, and DNA as it is known. A quiet quantum rule gives nature its chemical variety. It is the sort of rule one might easily overlook until noticing that it helps make almost everything interesting. The Pauli exclusion principle also helps explain something even more immediate: why matter feels solid. Atoms are mostly empty space by volume. The nucleus is tiny compared with the full size of the atom, and the electrons are described by spread out quantum orbitals rather than little hard shells. This raises a perfectly reasonable question. If matter is mostly empty space, why does a hand not pass straight through a table? Part of the answer is the electromagnetic force. Electrons have negative electric charge, and the electron clouds of atoms repel each other when pushed close together. When a hand presses against a table, the electrons in the atoms of the hand interact with the electrons in the atoms of the table. These electromagnetic interactions create resistance. The sensation of touch is not tiny solid balls making direct contact in the simple everyday sense. It is largely the result of electromagnetic forces between atoms and molecules. But the Pauli exclusion principle also plays a deep role. Because electrons cannot all occupy the same quantum state, the electron states of neighbouring atoms resist being forced into complete overlap. Compressing matter means trying to push electron wave functions into arrangements that quantum rules do not freely allow. This creates an additional resistance that helps matter occupy space and maintain structure. In many forms of matter, especially ordinary solids, the combination of electromagnetic repulsion and the exclusion principle helps produce the familiar experience of solidity. So when a hand rests on a wooden table, the hand is not meeting a perfectly filled block of substance. It is encountering a structured quantum system. The atoms in the hand and the atoms in the table are mostly space, but their electrons are organized by quantum states, governed by electric charge and constrained by Pauli's rule. The table pushes back because the underlying fields and particles do not permit matter to simply merge without resistance. This does not mean solidity is an illusion. It means solidity is not what it first appears to be. The surface feels firm because quantum physics and electromagnetism make it firm at the scale of human experience. The everyday feeling is real, but the explanation beneath it is stranger and more delicate than ordinary intuition suggests. The Pauli exclusion principle reaches far beyond tabletops. It helps explain the structure of atoms, the behavior of elements, the architecture of chemistry, and even the pressure supporting certain stars after they exhaust their nuclear fuel. In white dwarf stars, electron degeneracy pressure, rooted in the Pauli exclusion principle, helps resist gravitational collapse. The same quantum rule that helps give solidity to familiar matter also helps hold up stellar remnants. That is quite a career for a principle that began as a solution to atomic structure. The world you know depends on electrons not being allowed to become identical neighbours in the same state. It depends on layered atoms, organised orbitals, repeated chemical patterns, electromagnetic forces, and quantum restrictions hidden far below the senses. The reason a table feels solid is not because matter is packed full like a brick wall all the way down. It is because emptiness, charge, probability, and exclusion combine into something stable enough to lean on. Every firm surface is a quiet negotiation between particles and rules, and one of the most important rules is that electrons, in their own precise quantum way, refuse to all be the same. Chemistry is often introduced as the science of substances: water, salt, oxygen, carbon, metals, acids, medicines, fuels, and all the mixtures and materials that fill ordinary life. It can feel like a world of recipes, reactions, colours, smells, crystals, bubbling liquids, and the occasional school laboratory memory involving safety goggles that never quite sat properly. But beneath every chemical reaction is a deeper quantum story. Chemical bonds arise because electrons are quantum objects. Atoms do not join together like tiny sticky balls pressed into a model kit. They bond because their electrons can arrange themselves in ways that lower energy, satisfy quantum rules, and create stable patterns between nuclei. The shape of matter, the strength of materials, the behavior of water, the structure of DNA, the folding of proteins, and the design of medicines all depend on how electrons are shared, transferred, spread out, or weakly attracted between atoms. A covalent bond forms when atoms share electrons. This kind of bonding is central to molecules such as water, carbon dioxide, oxygen, and the long chains of carbon-based compounds that make life possible. The shared electrons are not simply sitting halfway between atoms like tiny beads on a string. They are described by quantum orbitals, spread out regions of probability shaped by the combined pull of more than one nucleus. When the arrangement is stable, a molecule can form. An ionic bond works differently. In ionic bonding, one atom effectively gives up one or more electrons while another gains them, creating charged particles called ions. These opposite charges attract. Sodium chloride, ordinary table salt, is the classic example. Sodium gives up an electron more easily, chlorine accepts one more readily, and the resulting sodium and chloride ions arrange themselves into a crystal lattice. The familiar little grains of salt are therefore built from electric attraction, quantum electron structure, and an impressive commitment to being sprinkled on chips. Metallic bonding is different again. In metals, outer electrons are not tied to one specific atom in the same way. They can become spread through the material, forming a mobile sea of electrons around positively charged atomic cores. This helps explain why metals conduct electricity and heat, why many metals can be bent or shaped without immediately shattering, and why they often have a distinctive shine. The gleam of copper, gold, aluminium, and iron is not just a surface detail. It reflects the behavior of electrons inside the material. Hydrogen bonds are weaker than covalent or ionic bonds, but they are enormously important. They form when hydrogen attached to an electronegative atom, such as oxygen or nitrogen, is attracted to another electronegative atom nearby. Hydrogen bonding helps give water many of its unusual properties, including its relatively high boiling point for such a small molecule and the way ice is less dense than liquid water. It also helps shape proteins and the double helix structure of DNA. A weaker bond can still have a very powerful career. Linus Pauling played a major role in explaining chemical bonding in quantum terms. His work on electronegativity, molecular structure, and the nature of the chemical bond helped connect chemistry with the new physics of electrons and orbitals. Electronegativity describes how strongly an atom attracts electrons in a bond. This idea helps explain why some bonds are evenly shared, why others are polar, and why molecules can have shapes and charge patterns that affect everything from dissolving in water to interacting with enzymes. Erwin Schrödinger's quantum mechanics helped transform chemistry from a science based mainly on observed patterns into one grounded in electron structure. Before quantum mechanics, chemists could describe how substances behaved, group elements in the periodic table, and develop powerful rules from experiment. But quantum mechanics explained why those patterns existed. It revealed that chemical properties emerge from electron arrangements, allowed energy states, molecular orbitals, and the principles governing how quantum particles behave. This quantum foundation reaches into almost everything nearby. Water bends into its familiar shape because of the arrangement of electrons around oxygen and hydrogen. Salt forms crystals because ions attract in ordered structures. DNA holds genetic information in molecules whose stability depends on covalent bonds, hydrogen bonds, and the geometry of atoms. Proteins fold into useful shapes because chemical bonds and intermolecular forces guide their structure. Minerals form from atoms arranged in repeating patterns. Plastics are long chains of bonded atoms. Medicines work because molecular shapes and charge distributions allow them to interact with proteins in the body. Carbon is especially important because of its electron structure. A carbon atom can form 4 covalent bonds, allowing it to build chains, rings, branches, sheets, and complex 3-dimensional molecules. This versatility makes organic chemistry possible. Carbon can bond with hydrogen, oxygen, nitrogen, phosphorus, sulfur, and other carbon atoms in countless arrangements. Life on Earth depends on this flexibility. The molecules of cells are not random piles of atoms. They are quantum-shaped structures built around carbon's remarkable bonding behavior. So the ordinary world is not built from atoms merely touching one another. It is built from quantum rules deciding how electrons may arrange themselves. Every flavor, medicine, plastic, mineral, cell, leaf, breath, and drop of water depends on those arrangements. Chemistry is quantum physics made tangible, turning invisible electron behavior into the substances of everyday life. The world is full of materials that seem to have their own personalities. Diamond is hard and clear. Graphite is soft and dark. Steel can carry the weight of bridges. Glass is rigid but fragile. Rubber bends and springs back. Ceramic can resist heat but crack under sudden impact. A cotton shirt feels soft against skin, while a silicon chip can quietly process information at astonishing speed. These differences feel so ordinary that it's easy to forget they need explaining. At the deepest level, the properties of materials depend on atomic structure, electron arrangement, crystal structure, and quantum bonding. The atoms matter, of course, but atoms alone are not enough. The same kind of atom can behave very differently depending on how it is bonded and arranged. The spacing between atoms, the shapes of electron orbitals, the allowed energy states of electrons, and the repeating patterns inside a solid all help decide whether a material is hard, soft, transparent, shiny, flexible, brittle, colourful, or electrically useful. Diamond and graphite make this point beautifully because both are made from carbon. In diamond, each carbon atom forms strong covalent bonds with 4 neighbouring carbon atoms in a rigid 3-dimensional network. This structure gives diamond its extraordinary hardness and high thermal conductivity. It is not magic sparkle dust, though jewellery adverts may respectfully disagree. It is carbon arranged in a very strong quantum bonded lattice. Graphite is also carbon, but its atoms are arranged differently. In graphite, carbon atoms form flat sheets of hexagonal patterns. Within each sheet, the bonds are strong, but the sheets can slide over one another more easily. That is why graphite is soft enough to leave marks on paper. A pencil does not write because carbon has one fixed personality. It writes because graphite's bonding arrangement allows thin layers to shear away. Same element, different structure, completely different material. This is one of the quiet lessons of quantum chemistry. Material properties are not just about what atoms are present, but how electrons allow those atoms to connect. A carbon atom in diamond and a carbon atom in graphite obey the same fundamental physics, but their electron arrangements produce different bonding geometries, change the bonding, and the world changes texture. The same logic helps explain conductors, insulators, and semiconductors. In a solid, especially a crystal, atoms are arranged in repeating patterns. The electrons in that repeating structure are not simply attached to isolated atoms. They're allowed energies spread into ranges called bands. Band theory is the quantum explanation for why some materials allow electric current to flow easily, while others resist it, and why semiconductors sit in the useful middle ground. Felix Bloch played an important role in developing the quantum theory of electrons in crystals. His work helped show how electrons behave in periodic crystal structures, where the repeating arrangement of atoms shapes the electrons' allowed wave-like states. In conductors such as copper, electrons can move through available energy states easily, allowing electric current to flow. In insulators such as glass or many ceramics, electrons are much more tightly restricted, so current does not flow easily. In semiconductors such as silicon, the energy structure can be controlled, which makes modern electronics possible. Colour also comes from quantum behaviour. Materials look coloured because they absorb, reflect, transmit or emit certain wavelengths of light. Electrons in atoms and molecules can absorb photons with specific energies, moving between allowed states. If a material absorbs some wavelengths and reflects others, the reflected light gives it colour. Plant chlorophyll absorbs strongly in red and blue parts of visible light, leaving much of the green light to be reflected or transmitted, which is why leaves often appear green. Pigments in paint and fabric work through their own molecular electron structures. Gemstones can owe their colours to impurities, crystal fields, and electron transitions within the material. Metals shine because their mobile electrons interact strongly with incoming light. This means colour is not simply painted onto the world. It is produced by the interaction between light and matter, between photons and electrons, between wavelengths and allowed energy states. A blue sapphire, a red ruby, a golden ring, a green leaf, and a glowing phone screen all reveal different ways quantum physics becomes visible. Everyday life is surrounded by these scaled-up quantum effects. Glass is transparent because its electron structure does not strongly absorb visible light. though it can absorb ultraviolet or infrared light more strongly. Steel is strong because iron atoms, carbon atoms, and crystal structures combine into durable arrangements. Ceramics resist heat because their bonding and atomic structures are often very stable. Rubber stretches because long molecular chains can flex, coil, and return. Fabrics feel different depending on the fibers, molecular structures, and surface textures involved. Coatings can repel water, reduce scratching, reflect heat, or absorb light because their microscopic structures and electron behavior have been engineered for those effects. A silicon chip is especially revealing. Silicon's semiconductor behavior depends on its crystal structure and quantum band gap. By carefully adding tiny amounts of other elements, engineers can control how electrons move through it. That controlled movement becomes logic, memory, images, sound, and calculation. The smooth glass screen and the tiny processor beneath it are both examples of quantum behavior turned into familiar material reality. So the world's textures are not accidental. Hardness, softness, transparency, color, flexibility, conductivity, and brittleness all come from deeper arrangements of atoms and electrons. The macroscopic world, the world that can be touched, worn, built with, polished, folded, scratched, and occasionally dropped on a kitchen floor, is shaped by quantum rules made large. Matter has character because electrons have rules. Materials feel different because atoms can be arranged differently. The ordinary world has strength, color, and texture because quantum behavior does not stay hidden. It rises into the hand, the eye, the wall, the screen, the fabric, the stone, and the quiet surface of everything nearby. The modern world often feels weightless. A message crosses the planet in a moment. A camera turns light into memory. A phone wakes at the touch of a finger. A car measures its own motion. A satellite listens quietly from orbit. A medical scanner builds images from signals the body could never reveal to the eye alone. It all seems like electricity made clever, but beneath that cleverness is quantum physics. Modern electronics depend on semiconductors, materials whose electrical behavior can be controlled with extraordinary precision. A semiconductor is not quite a conductor like copper, where electrons can move easily, and not quite an insulator like glass, where electrons are generally held in place. It sits in a useful middle ground. Its behavior depends on quantum band structure, the pattern of allowed and forbidden energy states available to electrons inside a solid. In a crystal, atoms are arranged in repeating patterns. Electrons do not behave as if each atom were completely isolated. Their allowed energies spread into bands across the material. In a conductor, electrons can move into available states with little difficulty, so electric current flows easily. In an insulator, there is a large energy gap between occupied states and available higher states, so electrons cannot move freely under ordinary conditions. A semiconductor has a smaller gap, one that can be engineered, controlled, and persuaded into usefulness with just the right treatment. Silicon became the central material of modern electronics because of its atomic structure, abundant stability, and useful semiconductor properties. Each silicon atom has 4 outer electrons and forms a crystal in which atoms bond in an orderly network. Pure silicon at very low temperatures would not conduct electricity well, because its electrons are mostly tied up in bonds. But at ordinary temperatures, and especially when carefully engineered, some electrons can move into higher energy states where they can help carry current. When an electron moves away from its usual bonding position, it can leave behind what physicists call a hole. A hole is not a tiny physical object in the same way an electron is, but it behaves like a positive charge moving through the material. This idea may sound like calling an empty parking space a vehicle, which is not recommended in traffic law, but in semiconductor physics, it is extremely useful. Electrons and holes allow current to be controlled inside silicon. The key process that makes semiconductors so powerful is doping, Doping means adding tiny amounts of other elements to a semiconductor to change its electrical behavior. Add an element with one more outer electron than silicon, such as phosphorus, and extra electrons become available for conduction. Add an element with one fewer outer electron, such as boron, and holes become available instead. The amount added can be extremely small, yet it can transform the material's behavior. A nearly pure crystal becomes a carefully tuned quantum landscape. This control made the transistor possible. In 1947, John Bardeen, Walter Brattain, and William Shockley at Bell Labs created the first working transistor. It was one of the most important inventions in technological history. The transistor could act as a tiny switch or amplifier, controlling one electrical signal with another. Earlier electronics often depended on vacuum tubes, which were larger, more fragile, hotter, and less efficient. Transistors allowed electronics to shrink, multiply, and become far more reliable. A transistor works because quantum physics allows electrons and holes to be guided through engineered regions of semiconductor material. By arranging differently doped regions together and applying voltages, a transistor can permit or block current or amplify a signal. In digital electronics, this switching becomes the basis of logic. On and off, states can represent information. Combine enough transistors, and the switching becomes calculation, memory, image processing, communication, and control. The scale is astonishing. Modern computer chips can contain billions of transistors, each one a tiny controlled region of semiconductor physics. They are not thinking because silicon has become magically intelligent. They are switching again and again in patterns designed by human engineering and made possible by quantum band structure. A phone, laptop, camera, smartwatch, car control system, or satellite is full of organized electron behavior. This reaches almost every part of modern life. Phones depend on semiconductor processors, memory chips, image sensors, radio systems, and display electronics. Computers depend on transistors arranged into circuits that perform logical operations at extraordinary speed. Digital cameras use semiconductor sensors that turn incoming photons into electrical signals. Medical devices use semiconductor electronic for imaging, monitoring, pacemakers, laboratory instruments, and hospital systems. Satellites rely on semiconductor components for communication, navigation, control, and observation. Cars now contain chips that help manage engines, braking systems, sensors, cameras, safety features, and navigation. Even the internet, which can feel almost invisible, rests on physical devices shaped by quantum rules. Data centers, routers, fiber optic transmitters, memory storage, processors, and communication systems all depend on electrons and photons behaving in ways engineers can control. The digital world is not floating above matter. It is matter, arranged with almost absurd precision. Semiconductors show how quantum physics shapes the world you know in the most practical sense. The same rules that explain atoms and energy levels become the rules behind screens, sensors, processors, and signals. The tiny gap between allowed energy bands becomes a doorway into modern civilization. Electricity powers the digital world, but quantum physics gives it structure. The transistor is not just a clever electrical component. It is a small, reliable agreement between human engineering and the deep behavior of electrons inside matter. Every tap on a screen, every saved photograph, every quiet notification, and every glowing pixel is carried by that agreement, hidden inside silicon, working without fuss, shaping modern life from beneath the surface. A beam of laser light feels almost too neat to be natural. Ordinary light spreads in every direction, scatters from lamps, bounces from walls, softens at the edges, and fills a room in a loose, forgiving way. A laser is different. It can travel as a narrow beam, hold a precise colour, cut through metal, scan a barcode, carry information through a fiber optic cable, or guide a surgeon's hand with microscopic accuracy. It is light behaving with unusual discipline, which is not something light was ever required to do. The reason lasers are possible comes from a quantum process called stimulated emission. Albert Einstein described the theoretical basis for emission and absorption in the early 20th century, showing that atoms and molecules could absorb and emit light in ways governed by quantum energy levels. When an atom or molecule is in an excited state, it can release energy by emitting a photon. In ordinary spontaneous emission, this happens randomly. The emitted photon may travel in any direction, with no particular agreement between one atom and another. This is the kind of behavior expected from a normal lamp. Useful, warm, and not especially organized. Stimulated emission is more orderly. If a photon with the right energy passes near an excited atom, it can trigger that atom to release another photon. The new photon matches the first one in energy, direction, phase, and frequency. In simple terms, the light becomes more coordinated. One photon encourages another to join it, and then that photon can help stimulate more. This produces a growing wave of highly organized light. A laser works by creating conditions where stimulated emission dominates. The word laser comes from light amplification by stimulated emission of radiation. The idea is slightly more elegant than the acronym sounds after being unpacked. A laser uses a gain medium, such as a gas, crystal, dye, or semiconductor, whose atoms or electrons can be excited into higher energy states. Mirrors often reflect the light back and forth through the medium, allowing more stimulated emission to occur. Eventually, a controlled beam escapes. That beam is coherent, meaning its waves are strongly aligned in phase. It is also usually narrow, focused, and sharply defined in color. This makes laser light very different from ordinary light. A light bulb sends out photons in many directions and at many wavelengths. The photons are not marching together. They are more like a crowd leaving a theatre after a long performance, each with a separate plan and varying confidence about where the car is parked. A laser beam, by contrast, is highly coordinated. Its photons are produced through quantum transitions that reinforce one another. That coordination makes lasers useful almost everywhere. Barcode scanners use laser light to read patterns of dark and light lines. Fiber optic communication uses laser pulses to send information through thin glass fibers, carrying internet data, phone calls, and video across continents and oceans. Eye surgery can use precisely controlled lasers to reshape tissue or treat parts of the retina. Manufacturing uses lasers for cutting, welding, engraving, measuring, and aligning materials. Blu-ray technology uses blue-violet laser light to read very small features on discs. Scientific measurement uses lasers to detect tiny distances, cool atoms, study molecules, and even help observe gravitational waves in instruments such as the Laser Interferometer Gravitational Wave Observatory. Lasers are one form of quantum control over light, but glowing screens reveal another. Light-emitting diodes, often called LEDs, work through quantum behavior inside semiconductor materials. In a light-emitting diode, electrons and holes recombine. When an electron falls into a lower energy state by filling a hole, energy can be released as a photon. The color of the photon depends on the energy difference between the states involved, which is controlled by the semiconductor material. Nick Holonyak Jr. is widely associated with the first practical visible light-emitting diode, developed in the early 1960s. Since then, light-emitting diode technology has transformed how the modern world glows. Traffic lights, car lights, street lighting, televisions, computer monitors, decorative lighting, phone screens, and countless indicators on devices all use carefully engineered semiconductor materials to produce light efficiently. In a screen, this quantum process becomes color and image. Different materials or device structures produce red, green, and blue light, and those colors are combined in varying intensities to create the impression of almost every colour the eye can see. The glowing image on a phone or television is not painted there in any ordinary sense. It is built from controlled photon emission, guided by electrical signals, semiconductor design, and quantum transitions between energy states. The same is true of many modern displays. Organic light-emitting diodes use carbon-based molecules or polymers that release photons when electrical energy moves charges through them. Liquid crystal displays often use backlights, filters, and controlled light transmission, while the light source behind them may still depend on quantum semiconductor devices. However the exact screen is built, the visible result depends on the interaction between electrons, energy levels, materials, and photons. So the visible world of modern technology rests on light being controllable at the quantum level. A laser beam in a scanner, a signal in a fibre optic cable, the glow of a television, the colour of a traffic light, and the brightness of a phone screen all come from the same deeper fact. Electrons and atoms can move between allowed energy states and release photons in predictable ways. The world now shines through engineered quantum behaviour. It is not merely lit by electricity, it is lit by transitions, bands, photons, semiconductors, and stimulated emission. Every glowing pixel and precise beam is a small reminder that quantum physics does not only explain the hidden world beneath reality, it also illuminates the world directly in front of the eye. Heat feels simple because the body understands it before the mind has to. A warm mug in the hand, sunlight on skin, the sudden sharp heat from an oven door, the coolness of a window at night, the comforting warmth of a blanket. These are ordinary sensations, familiar and immediate. But beneath them is a restless, microscopic world. Temperature is not a substance that flows into things like invisible honey. It's connected to the motion, vibration, rotation, and energy of atoms, molecules, electrons, and particles inside matter. In a gas, temperature is closely related to the average motion of its molecules. Heat the air, and its molecules move faster on average. Cool it down, and they move more slowly. In a liquid, molecules are still moving and jostling, but they remain close enough to pull on one another. In a solid, atoms are usually held in place within a structure, yet they are not perfectly still. They vibrate around their positions like tiny restless neighbours who have agreed not to leave the street but refuse to stand completely motionless. Thermodynamics describes heat, temperature, energy, and work at the scale of everyday experience. It explains why heat flows from hotter objects to colder ones, why engines have limits, why refrigerators need energy to move heat the wrong way, and why a cup of tea cools down if left alone, no matter how emotionally attached one may be to its original warmth. Thermodynamics remains essential because it works beautifully for large systems with huge numbers of particles. But quantum physics explains the microscopic exchanges beneath those broad rules. One important example is heat capacity. Heat capacity describes how much energy must be added to raise the temperature of a material. Different substances warm up differently because their internal structures store energy in different ways. Water can absorb a great deal of heat before its temperature changes much, which helps stabilize climates and makes oceans slow to warm and cool. Metals often heat and cool more quickly. Solids, gases, and liquids all store energy through the motions and arrangements available to their particles. Classical physics once struggled to explain heat capacity fully. It predicted some patterns correctly in certain conditions, but it failed at low temperatures, especially for solids. Experiments showed that the heat capacity of many solids decreased as temperature fell, rather than staying at the constant value classical theories expected. This was another sign that energy inside matter was not being stored in a perfectly smooth classical way. Albert Einstein made an important step in 1907 by applying quantum ideas to the heat capacity of solids. He treated atoms in a solid as quantum oscillators, able to vibrate only with certain allowed energies. This helped explain why heat capacity changes at low temperatures. Peter Debye later improved the model by treating vibrations in a solid, in a more collective way, giving a more accurate account of how heat capacity behaves as temperature changes. These models show that even something as familiar as warming a solid could require quantum physics underneath. The key idea is that vibrations in a crystal lattice can be quantized. In a solid crystal, atoms are arranged in a repeating pattern. They can vibrate together, passing energy through the material in wave-like patterns. Quantum physics describes these vibrations in terms of phonons. A phonon is a quantized unit of vibrational energy in a material. It is not a tiny bead bouncing between atoms. It is more like a packet of organized vibration, a quantum description of how sound and heat can move through a lattice. This can be connected gently to sound. Sound is a vibration moving through matter. In a solid, atoms pull on one another, so a disturbance can travel through the structure. At the quantum level, those vibrational patterns have allowed energies. Phonons help explain how heat moves through many solids, how materials store thermal energy, and why some substances conduct heat well while others do not. Metals often conduct heat efficiently, partly because both electrons and lattice vibrations can carry energy. This is why a metal spoon in a hot pan becomes unpleasantly educational very quickly. Insulating materials, by contrast, are structured in ways that slow the movement of heat. Foams, fabrics, trapped air pockets, and certain ceramics reduce the transfer of thermal energy, helping keep buildings warm, hands protected, or spacecraft shielded from extreme temperature differences. Quantum heat behavior also matters in electronics. Computer chips generate heat because electrical energy is not used perfectly. As electrons move through circuits, energy is transferred into the material, often as vibrations in the lattice. Cooling electronics is therefore not just a matter of fans and metal fins, although those help. It also depends on how heat is carried through materials at microscopic scales. Engineers designing processors, sensors, lasers, and power electronics must care deeply about thermal conductivity, electron behavior, phonons, and the movement of energy through solids. Cooking also belongs to this wider story. Heat changes molecules. It denatures proteins, melts fats, evaporates water, breaks chemical bonds, forms new compounds, and transforms textures and flavors. The browning of bread, the setting of an egg, the softening of vegetables, and the melting of chocolate all depend on thermal energy changing molecular motion and chemical structure. The kitchen may look less like a physics laboratory, mostly because it has more crumbs, but matter is still obeying the same hidden rules. Thermal radiation brings the story back to light. Warm objects emit electromagnetic radiation. At ordinary temperatures, much of this is infrared light, invisible to human eyes but detectable as heat. As objects become hotter, they can glow red, orange, yellow, or white. This glow depends on quantum exchanges of energy and on the relationship between temperature and emitted radiation. A stove element, a candle flame, hot metal, molten lava, and stars all reveal heat through light. So heat is both familiar and deeply layered. At everyday scales, thermodynamics describes its flow with remarkable power. At microscopic scales, quantum physics explains how energy is stored, exchanged, vibrated, emitted, and carried through matter. Warmth is not one simple thing. It is the large-scale feeling of countless small motions and quantum-allowed exchanges. Every warm object is full of activity. Every cool surface is still vibrating faintly. Every glowing ember, insulated wall, metal pan, electronic chip, and living body depends on the same hidden relationship between energy and matter. Temperature is what that motion becomes when the world is viewed from far enough away to feel calm, continuous, and ordinary. Some barriers in life are wonderfully straightforward. A wall stops a person. A locked door stops a visitor. A hill slows a cyclist. A fence discourages the neighbour's cat, at least in theory. In the everyday world, if something does not have enough energy to cross a barrier, it usually remains on the side where it started. Classical physics treats this very sensibly. A ball rolling toward a hill either has enough energy to go over the hill, or it rolls back down with a certain quiet embarrassment. Quantum physics adds a stranger possibility. Quantum tunneling is the process by which a quantum particle has a chance of appearing on the other side of a barrier that it could not cross according to classical physics. It does not mean the particle smashes through the barrier like a tiny heroic miner. It does not mean the barrier secretly opens a little door. It means the particle's quantum wave function can extend into and sometimes beyond the barrier, giving a real probability that the particle may be detected on the far side. This idea sounds as if it should belong to fantasy, but it is a standard part of quantum mechanics. In classical physics, a particle with too little energy to overcome a barrier is simply stuck. In quantum physics, the particle is described by a wave function, and that wave function does not always stop sharply at the edge of the barrier. It can fade into the forbidden region. If the barrier is thin enough and the circumstances are right, part of the wave function can reach the other side. When a measurement is made, there is a chance the particle will be found beyond the barrier. The important word is chance. Tunneling is probabilistic, not guaranteed. It is also overwhelmingly a feature of very small systems such as electrons, protons, atomic nuclei, and other quantum particles. A person cannot casually tunnel through a wall, no matter how late they are or how committed they feel. The probability for a large everyday object to tunnel through a macroscopic barrier is so absurdly tiny that it can be treated as impossible for all practical purposes. Quantum tunneling does not make furniture unreliable. The sofa will remain in the room, possibly forever, depending on how difficult it is to move. At small scales, though, tunneling matters enormously. One of the most important examples is nuclear fusion in the Sun. The Sun shines because light atomic nuclei fuse together in its core, releasing energy. The main process begins with hydrogen nuclei, which are simply protons. But protons carry positive electric charge, and positive charges repel each other through the electromagnetic force. To fuse, two protons must get extremely close enough for the strong nuclear force to bind them. Classically, many protons in the Sun's core would not seem to have enough energy to overcome their electric repulsion, often enough to explain the Sun's steady brightness. Quantum tunneling helps solve this. The protons do not always need to climb fully over the repulsive energy barrier in the classical sense. Their wave functions give them a small chance of tunneling through that barrier and coming close enough for fusion to begin. Each individual chance is tiny, but the Sun contains an enormous number of protons, and its core is hot and dense. Across that vast population, enough tunneling events occur to help power the sunlight that reaches Earth. This means the warmth on skin, the daylight through a window, the energy behind weather, photosynthesis, food chains, and almost all life on Earth are connected to quantum tunneling. The Sun is not shining because particles politely obey ordinary barrier rules. It shines partly because quantum probability permits rare events that become powerful when repeated on a stellar scale. Quantum tunneling also explains radioactive alpha decay. In alpha decay, an atomic nucleus emits an alpha particle made of two protons and two neutrons. Classically, that alpha particle can be trapped inside the nuclear potential barrier, but quantum mechanically, it has a probability of tunneling out. George Gamow helped explain alpha decay using quantum tunneling in the late 1920s, showing how the measured lifetimes of radioactive nuclei could be understood through this strange escape mechanism. The alpha particle does not simply burst through the barrier by brute force. It has a quantum chance of being found outside it. The same principle has practical uses in technology. A scanning tunneling microscope uses tunneling to image surfaces at the level of individual atoms. A very sharp conducting tip is brought extremely close to a surface, so close that electrons can tunnel between the tip and the sample. The tunneling current changes sensitively with distance, allowing the instrument to map tiny surface features. This has given scientists a powerful way to study atoms, molecules, and materials with extraordinary precision. Tunnel diodes also use tunneling. These electronic components allow current to pass through a barrier in a way that depends on quantum mechanics, giving them unusual electrical properties useful in certain high-speed applications. Flash memory, used in devices such as phones, cameras, and solid-state drives, also relies on quantum tunneling in controlled ways. Electrons can be moved through thin insulating barriers to store information as charge. The result is memory that can remain even when power is switched off. A saved photograph, message, or document may owe part of its survival to electrons doing something classically forbidden. Tunneling can also appear as both a useful feature and a challenge in modern electronics. As devices become extremely small, electrons may tunnel through barriers where engineers would prefer them not to. At tiny scales, insulation is not always as absolute as it seems in the everyday world. This is one reason designing smaller and smaller circuits becomes increasingly difficult. Quantum behavior is not an optional extra waiting politely in a textbook. It turns up inside the hardware. Quantum tunneling is one of the clearest examples of how quantum physics shapes the world you know. It helps explain radioactive decay, contributes to the fusion reactions that make the sun shine, enables instruments that can see individual atoms, and supports technologies that store information. It is not about large objects casually passing through walls. It is about the wave-like nature of quantum particles creating possibilities that classical physics would forbid. The ordinary world remains stable because large objects almost never tunnel in any noticeable way. But deep beneath that stability, tiny particles sometimes pass where they should not classically pass. From sunlight to memory chips, from nuclear physics to atomic-scale microscopes, reality quietly uses hidden routes through barriers. The world does not merely go over obstacles. At its smaller scales, sometimes it goes through. Magnetism feels like one of nature's quiet tricks. A fridge magnet clings to a door. A compass needle turns toward north. A speaker turns electrical signals into sound. An electric motor spins. A medical scanner looks inside the body without needing to open it. These things can feel familiar enough to seem almost simple, but magnetism is not just a mysterious pull hiding inside metal. At its deepest level, much of it depends on quantum physics, and especially on a property called spin. Electron spin is an intrinsic quantum property. The name is slightly misleading, because an electron is not simply a tiny solid ball physically spinning like a planet or a toy top. Spin is more fundamental than that. It behaves mathematically like angular momentum, and it gives electrons a magnetic character. But it should not be imagined too literally as a little charged marble whirling around. Quantum physics often borrows words from the everyday world, then quietly makes them stranger. An electron has electric charge, and because of its spin, it also acts a little like a tiny magnet. In atoms, the arrangement of electrons matters enormously. Electrons fill quantum states according to rules such as the Pauli exclusion principle, and their spins can pair up or remain unpaired. When electron spins are paired in opposite directions, their magnetic effects often cancel. When unpaired spins remain, an atom or ion can have a magnetic moment. The way these magnetic moments interact across a material helps decide whether that material responds strongly, weakly, or almost not at all to magnetic fields. One of the most important early demonstrations of spin-related quantum behavior came from the Stern-Gerlach experiment. In the early 1920s, Otto Stern and Walter Gerlach sent a beam of silver atoms through a non-uniform magnetic field. Classical expectations suggested that the atom's magnetic orientations might spread into a continuous smear. Instead, the beam split into distinct parts. This showed that angular momentum behavior at the atomic scale was quantized. The result became one of the key signs that microscopic magnetism did not obey the smooth expectations of classical physics. Different materials respond to magnetic fields in different ways because their electron structures differ. Ferromagnetism is the strong form of magnetism, seen in materials such as iron, cobalt, and nickel. In ferromagnetic materials, neighbouring magnetic moments can align with one another across regions called domains. When many domains line up, the material can become strongly magnetic. A fridge magnet, a permanent magnet, and many magnetic tools rely on this kind of organised alignment. Paramagnetism is weaker. In paramagnetic materials, atoms or ions have unpaired electrons, so they are attracted to magnetic fields, but their magnetic moments do not usually remain strongly aligned after the external field is removed. The effect is real but gentle. Diamagnetism is different again. It occurs in all materials to some degree, and involves a weak tendency to oppose an applied magnetic field. In many materials, diamagnetism is hidden by stronger magnetic effects, but in substances with no unpaired electrons, it can be the main magnetic response. These categories may sound technical, but they shape familiar objects. Fridge magnets depend on ferromagnetic or related magnetic materials that can hold an aligned magnetic pattern. Electric motors use magnetic fields to turn electrical energy into motion, allowing fans, washing machines, drills, pumps, and countless hidden mechanisms to work. Speakers use changing magnetic fields to move a coil or diaphragm, turning electrical signals into pressure waves in air. Hard drives store information by controlling magnetic regions on a surface. Though many newer storage technologies use different physical principles, compasses align with Earth's magnetic field, a planetary scale field generated by motion in Earth's liquid outer core, and they turn that enormous geophysical process into a small needle quietly pointing the way. Magnetism also reaches into medicine through nuclear magnetic resonance and magnetic resonance imaging. Atomic nuclei can have spin, not just electrons. The hydrogen nuclei in water and fat inside the body are especially useful in medical imaging because the body contains so much hydrogen. In a strong magnetic field, these nuclear spins can align in particular ways. Radio wave pulses then disturb that alignment, and as the nuclei return toward equilibrium, they produce signals that can be detected and processed into images. Magnetic resonance imaging is one of the clearest examples of abstract quantum properties becoming practical and visible. The machine is large, loud, and not exactly famous for its relaxing soundtrack, but the underlying idea is subtle. It uses quantum spin properties of atomic nuclei, powerful magnets, radio waves, and careful signal processing to create detailed images of soft tissues, organs, blood vessels, joints, and the brain. A property that sounds almost impossibly small becomes a tool for seeing inside the living body. The same quantum foundations matter in scientific research and technology more broadly. Magnetic materials are used in sensors, memory devices, generators, transformers, microphones, headphones, credit cards, security systems, and laboratory instruments. Engineers and physicists design materials by understanding how electron spins, crystal structures, and quantum interactions shape magnetic behavior. The ordinary click of a magnet, the turning of a motor, and the image from a medical scanner all belong to the same deeper story. Spin is not visible to the eye. No one looks at an electron and sees it turning like a tiny moon. Yet spin has consequences that rise into the everyday world. It helps create magnetism, shapes materials, enables technologies, and allows information to be measured, stored, moved, and transformed. The world you know is full of invisible alignments. Some are inside metals, some are inside machines, some are inside the nuclei of atoms in the body. Magnetism is not only a force felt between objects, it is quantum structure made practical, a hidden compass inside matter that turns abstract rules into motion, sound, memory, direction, and images of life itself. Most quantum behavior is hidden from ordinary sight. It lives in atoms, electrons, photons, energy levels, and probability patterns far too small for the senses to detect directly. But sometimes, under very special conditions, quantum physics stops being merely microscopic. It rises into view. It becomes a levitating magnet, a current that refuses to fade, a liquid that flows without ordinary resistance, or a machine powerful enough to look inside the human body. Superconductivity is one of the clearest examples. It is a state in which electrical resistance disappears in certain materials, usually at very low temperatures. In an ordinary wire, electrons moving through a metal encounter resistance. They scatter from vibrations in the lattice, impurities, and other disturbances, losing energy as heat. This is why electrical devices warm up, why power lines waste some energy, and why a laptop can become hot enough to suggest it is quietly attempting re-entry from orbit. In a superconductor, that ordinary resistance vanishes. Electric current can flow without the usual energy loss. If a current is set moving in a superconducting loop, it can persist for an extraordinarily long time. This is not because the electrons have become magically frictionless little marbles. It is because the material has entered a collective quantum state, where many particles behave together in a deeply organized way. Superconductivity was discovered in 1911 by Heike Kamerlingh-Onnes, a Dutch physicist who had also achieved the liquefaction of helium. While studying mercury at extremely low temperatures, he found that its electrical resistance suddenly dropped to essentially zero. This was completely unexpected. Classical physics could not explain why a metal should abruptly lose resistance below a critical temperature. Something new was happening inside matter. The quantum explanation for conventional superconductivity came much later through the Bardeen-Cooper-Schrieffer theory, named after John Bardeen, Leon Cooper, and John Robert Schrieffer. The key idea involves Cooper pairs. Under the right conditions, electrons in a material can form paired states through their interaction with vibrations in the crystal lattice. This sounds odd, because electrons normally repel each other due to their negative electric charge. But in a cold lattice, an electron can slightly distort the positive atomic framework around it, and another electron can be influenced by that distortion. The result is an effective attraction that allows electrons to pair up. These Cooper pairs do not behave like separate ordinary electrons. They enter a shared quantum state, moving collectively through this material. Because the paired electrons are organized into this coherent state, they can travel without scattering in the usual resistance-producing way. The material becomes superconducting. Superconductors also produce striking magnetic effects. They can expel magnetic fields from their interior, a phenomenon called the Meissner effect. This allows magnetic levitation under the right conditions, where a magnet can hover above a superconductor, or a superconductor can remain suspended near a magnet. It is one of those rare moments when quantum physics looks exactly as strange as it sounds. A calm little piece of matter appears to ignore ordinary expectations, as if it has read the rulebook and found a footnote. These properties are not only beautiful demonstrations, they are technically powerful. Superconductors can create extremely strong magnetic fields, which are essential in magnetic resonance imaging machines. These scanners rely on powerful superconducting magnets to help produce detailed images of tissues inside the body. Superconductors are also used in particle accelerators, where strong magnets guide and focus beams of particles. Facilities such as the Large Hadron Collider at the European Organisation for Nuclear Research depend on superconducting magnet technology to keep particles moving around enormous circular paths. Superconductivity also matters in quantum devices, including some forms of quantum computing. Superconducting circuits can be engineered so that electrical currents and energy states behave quantum mechanically in controlled ways. Research groups around the world use superconducting qubits as one approach to building quantum processors. Superconductors are also explored for experimental power technologies, including efficient transmission lines, magnetic energy storage, and advanced motors, although the need for low temperatures remains a major practical challenge. Another dramatic example of collective quantum behavior is superfluidity. Superfluidity appears in substances such as liquid helium when cooled to extremely low temperatures. liquid helium can enter a state where it flows with no ordinary viscosity. It can creep along surfaces, pass through tiny openings, and behave in ways no ordinary liquid should. Again, this does not mean it has become enchanted, even if it seems to be doing a convincing impression. It means a large number of atoms have entered a collective quantum state. Helium is especially important because it remains liquid at temperatures where many substances would be solid. Helium-4, when cooled below a critical temperature, can become a superfluid. In this state, quantum behavior is no longer hidden inside a single atom. It shapes the motion of the whole liquid. Superfluid helium helped physicists understand how quantum mechanics can govern collective systems, not just isolated particles. These phenomena reveal something important about the world. Quantum physics is not always confined to invisible scales. Usually quantum behavior is hidden because ordinary objects are warm, noisy, and full of countless interactions with their surroundings. Delicate quantum patterns become blurred into classical behavior. But when matter is cooled, isolated, purified, and arranged in the right way, quantum rules can become visible at a macroscopic scale. Superconductors and superfluids show matter behaving collectively, as if vast numbers of particles have agreed to follow one shared quantum rhythm. The result can be resistance-free current, powerful magnets, levitation, persistent flow, and liquids that ignore ordinary viscosity. These are not violations of nature's laws. They are nature's laws revealed under unusual conditions. The familiar world is usually too warm and busy to display such behavior openly. But beneath ordinary materials, the same quantum rules remain. Under the right circumstances, they rise into view, turning hidden mathematics into hovering magnets, silent currents, and liquids that flow as though friction has quietly gone to sleep. Life feels warm, wet, restless, and beautifully complicated. It grows, breathes, repairs itself, eats, responds, remembers, and turns sunlight into leaves, flowers, fruit, forests, and the occasional houseplant that seems determined to make its owner feel judged. At first glance, biology can seem far away from quantum physics. Living things are soft and messy. Quantum physics is usually imagined as cold, precise, microscopic, and surrounded by equipment that looks expensive enough to require its own insurance policy. But life is made of molecules, and molecules are made of atoms. Atoms are governed by quantum physics. So in one basic sense, biology has always depended on quantum rules, chemical bonds, electron arrangements, molecular shapes, energy levels, and the behavior of photons all shape the machinery of living cells. Breathing, metabolism, vision, growth, nerve signaling, photosynthesis, digestion, and the folding of proteins all depend on molecules behaving according to quantum chemistry. Quantum biology is the careful study of where quantum effects may play especially meaningful roles in living systems. The word careful matters. It is easy to overstate this subject and make it sound as though life is powered by vague quantum magic. That is not the scientific picture. Biology is not mysterious because someone has sprinkled the word quantum over it like glitter. The real question is more precise. Are there places where living systems use, preserve, or are influenced by quantum effects in ways that matter for their biological function? One of the most studied examples is photosynthesis. Plants, algae, and some bacteria capture energy from sunlight and use it to help build chemical energy. The first step happens in light harvesting complexes, where molecules absorb photons and transfer energy toward reaction centers. That energy transfer is remarkably efficient in many photosynthetic systems. Researchers have investigated whether quantum coherence may play a role in helping energy move through these molecular structures. Graham Fleming and colleagues at the University of California, Berkeley, carried out important experimental work on quantum coherence in photosynthetic complexes. Quantum coherence means that a system can show wave-like relationships between possible states, at least for a short time. In the context of photosynthesis, the idea is that absorbed energy may not move through the complex like a tiny classical ball, hopping blindly from molecule to molecule. Instead, under some conditions, it may explore possible pathways in a more wave-like quantum manner before reaching a useful destination. This does not mean a leaf is doing conscious quantum computing in the garden. The leaf is already busy enough. It means that parts of photosynthetic energy transfer may involve quantum behavior that helps explain how energy moves so effectively through molecular systems. The details remain an active area of research, and scientists are careful about exactly how long coherence lasts, how important it is under natural biological conditions, and how much it contributes to the overall efficiency of photosynthesis. Another area where quantum effects can matter is enzyme catalysis. Enzymes are biological molecules, usually proteins, that speed up chemical reactions. Life depends on enzymes because many reactions needed for metabolism would otherwise happen far too slowly. In some enzyme reactions, protons or electrons may move by quantum tunneling. Tunneling allows a quantum particle to have a chance of passing through an energy barrier it could not classically cross. In biology, this can influence reaction rates and help explain how certain chemical transformations occur inside cells. This is not separate from ordinary life. Metabolism, respiration, digestion, and cellular repair are all built from chemical reactions. The body is not a simple machine with gears and levers. It is a vast molecular network where electrons shift, bonds form and break, energy is transferred, and enzymes guide reactions with astonishing specificity. Quantum rules are not optional here. They are part of the reason molecules have the shapes and behaviors that biology depends on. Magnetoreception in birds is another fascinating possible example. Many migratory birds appear able to sense Earth's magnetic field, helping them navigate over long distances. One proposed mechanism involves radical pairs of molecules with unpaired electrons, whose spin states may be influenced by magnetic fields. Klaus Schulten and Thorsten Ritz are closely associated with this radical pair model of avian magnetoreception. The idea is that quantum spin behavior could affect chemical reactions in light-sensitive proteins, possibly giving birds information about magnetic direction. This remains a frontier area. Evidence supports the idea that some animals can detect magnetic fields, and radical pair chemistry is a serious scientific model, but the full biological mechanism is still being investigated. It should be presented with caution. The point is not that birds have a mystical inner compass powered by cosmic vibes. The point is that quantum spin, chemistry, light, and biology may meet in a subtle way inside living tissue. Vision is another everyday reminder that life depends on quantum events. When light enters the eye, photons are absorbed by molecules in the retina. In rod cells, a molecule called retinal changes shape after absorbing a photon, triggering a chain of biochemical signals that eventually becomes visual information. Seeing begins when quantum packets of light interact with molecular machinery. The view of a face, a star, a candle, or a glowing screen begins with photons and electrons behaving according to quantum rules. Food also belongs to this story. Plants use sunlight to build energy-rich molecules. Animals eat plants or other animals. Cells break down molecules and transfer energy through controlled chemical pathways. Breathing brings oxygen into the body, where it helps extract energy from food through cellular respiration. Every step depends on molecular structure, electron transfer, enzyme function, and quantum-shaped chemistry. So quantum biology must be held in two ideas at once. The established foundation is that all biology rests on quantum chemistry, because molecules and electrons obey quantum physics. The more cautious frontier is the study of special quantum effects such as coherence, tunneling, and spin-dependent chemistry that may play particular functional roles in living systems. Life is not magically quantum in a vague sense. It is physically quantum in a precise sense. The living world grows from molecules, and molecules grow from quantum rules. Every breath, leaf, heartbeat, enzyme, eye, seed, and cell is part of that deeper continuity. Biology is not separate from physics. It is physics made soft, organised, self-repairing, and briefly awake. By this point, the world has already become much stranger than it first appeared. Light is made of photons, but it also behaves like a wave. Electrons can be detected as particles, yet they also have wave-like behaviour. Atoms hold together because electrons occupy quantum states rather than tiny classical orbits. Chemistry, colour, magnetism, heat, electronics, and even parts of biology all depend on invisible rules that do not resemble ordinary experience. But modern physics goes deeper still. The most complete framework for describing particles and their interactions is not simply quantum mechanics on its own, but quantum field theory. In quantum field theory, particles are not treated as tiny solid beads moving through empty space. Instead, they are understood as excitations of underlying fields. A field is something that exists throughout space and time, with values and possible activity at every point. A particle can be thought of as a ripple, disturbance, or packet of energy in one of these fields. This is a difficult idea because everyday life encourages a particle picture. A grain of sand is here rather than there. A drop of water lands in one place. A pebble can be held in the hand. So it is tempting to imagine electrons, photons, and other particles as smaller versions of those familiar objects. Tiny specks in emptiness. Little beads moving through the cosmic room. Quantum field theory changes that picture. The electron is associated with an electron field. The photon is associated with the electromagnetic field. Other particles have their own fields as well. What appears as a particle is a localized excitation of a field that extends across space-time. The field is the deeper object in the theory. The particle is how that field shows itself in a measurable event. This does not mean particles are unreal. It means particles are not necessarily the most basic way to describe reality. A wave on the surface of water is real, but it is not separate from the water. In a loose comparison, a particle is real as an excitation of a field. The comparison is not perfect, because quantum fields are not ordinary substances sloshing around in space, but it gives the mind somewhere gentle to rest for a moment before the furniture starts floating again. One of the greatest triumphs of quantum field theory is quantum electrodynamics, the theory describing interactions between light and charged particles. Quantum electrodynamics explains how electrons and photons interact, how charged particles emit and absorb light, and how electromagnetic forces operate at the quantum level. It is one of the most precisely tested theories in the history of science. Several major figures helped build this theory. Paul Dirac developed a relativistic quantum theory of the electron and predicted the existence of antimatter, including the positron. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga developed powerful formulations of quantum electrodynamics in the mid-20th century, each contributing to the theory's extraordinary success. Freeman Dyson showed how important approaches within the theory were connected, helping clarify its mathematical structure. Together, their work turned the interaction of light and matter into one of the sharpest tools in modern physics. Quantum electrodynamics helps explain many things that are not distant or exotic. It underlies the interaction between electrons and photons, which means it sits beneath atomic spectra, chemical bonding, light emission, electrical behavior, and the stability of matter. The glow of a lamp, the color of a material, the behavior of electrons in a semiconductor, and the way atoms interact with light all connect back to the quantum description of electromagnetism. This is where the deeper layer beneath particles becomes directly relevant to ordinary life. Electromagnetism is not just the force behind lightning and magnets. It is the interaction that shapes atoms, molecules, solids, electricity, chemistry, and light. Almost everything touched in everyday life is held together, mostly through electromagnetic interactions between charged particles. Those interactions are described most deeply by quantum field theory. A wooden table, a glass of water, a phone screen, a cotton shirt, a steel bridge, and a human hand do not require anyone to switch on a particle accelerator before they can exist. They are already made from atoms whose behavior depends on quantum fields and their interactions. Particle accelerators reveal the deeper structure by creating conditions where fields can show new excitations, new particles, or rare interactions. But they are not creating quantum fields from nothing. They are probing what is already there. The standard model of particle physics is the broader framework that describes known elementary particles and three of the fundamental interactions: the electromagnetic interaction, the weak nuclear interaction, and the strong nuclear interaction. Gravity is not included in the standard model in the same quantum field theory form, and that remains one of the great open problems in physics. The standard model includes particles such as quarks, leptons, gauge bosons, and the Higgs boson, each connected to fields and interactions. The European Organisation for Nuclear Research, often known by its historic name CERN, has played a central role in testing the standard model. Its particle accelerators, including the Large Hadron Collider, allow physicists to collide particles at extremely high energies and study the results. One of the most famous achievements was the discovery of the Higgs boson in 2012, confirming a major part of the theory connected to the Higgs field and the origin of mass for certain elementary particles. This may sound far removed from everyday reality, but it is not disconnected from it. The Higgs field is part of the field structure of the universe. The electromagnetic field shapes atoms and light. The strong nuclear interaction holds atomic nuclei together. The weak nuclear interaction plays an important role in radioactive decay and nuclear processes in stars. The ordinary world is not built on a separate set of ingredients from particle physics. It is the quiet, low-energy arrangement of those ingredients into stable forms. Quantum field theory does not make reality less physical. It makes physical reality deeper than the older particle picture. The world is not empty space filled with tiny beads. It is a layered structure of fields, excitations, interactions, probabilities, and stable patterns. At human scales, these deeper structures blend into the familiar world of objects, colours, textures, warmth, and weight. The chair, the air, the body, the light in the room, and the device glowing nearby all sit on top of this field-based reality. They do not look like quantum fields, because the everyday world is the softened surface of enormous numbers of interactions. But beneath every surface, the fields remain. Particles are what the fields show us when they are disturbed in particular ways. Matter is what those disturbances become when they settle into stable structures. And everyday reality is what emerges when the deeper quantum fields of the universe arrange themselves into something calm enough to touch. Reality usually looks settled before anyone asks questions about it. A cup is on the table, a shadow falls across the floor. A hand reaches for a phone and finds it exactly where it was left. The world does not appear to hover between possibilities. It appears definite, stable, and very committed to being itself. That is one of the reasons quantum physics can feel so strange. It suggests that beneath the steady surface of ordinary life, nature is not always described by definite properties waiting quietly to be discovered. In quantum mechanics, one of the central ideas is the wave function. The wave function is a mathematical object used to describe the possible states of a quantum system. It can contain information about where a particle might be found, what momentum it might have, what energy state it may occupy, or how several possible outcomes relate to one another. It is not simply a little cloud painted around a particle, although cloud images can sometimes be helpful. It is a precise mathematical description of possibilities, probabilities, and quantum relationships. This was one of the great shifts in physics. Classical physics often imagines that objects have definite properties whether or not anyone is looking. A stone has a position, a planet has a path, a thrown ball follows a trajectory. Even if a measurement is imperfect, the underlying assumption is that the object really had exact values all along. The job of science is to measure them more accurately, ideally without dropping the instrument, which is always a respectable ambition. Quantum mechanics changed that expectation. In many situations, it does not simply assign a particle one definite classical property before measurement. Instead, it gives probabilities for possible outcomes. Max Born made this interpretation central by arguing that the wave function should be understood probabilistically. The wave function does not tell us exactly what result will occur in a single measurement. It tells us the likelihood of different results. Repeated many times under the same conditions, the outcomes follow the probabilities predicted by quantum mechanics with extraordinary accuracy. This does not mean quantum mechanics is vague. In fact, it is one of the most precise scientific theories ever developed. The probabilities it gives are not loose guesses. They are mathematically exact within the theory and have been tested with remarkable success. The strangeness is not that quantum physics cannot predict anything. The strangeness is that what it predicts most directly is a pattern of possible outcomes, not always one fixed classical fact waiting patiently behind the curtain. Werner Heisenberg sharpened this picture with the uncertainty principle. The uncertainty principle says that certain pairs of physical properties, such as position and momentum, cannot both be defined with unlimited precision at the same time. This is often misunderstood as a problem of poor measurement, as if a better microscope could solve everything if only someone cleaned the lens properly. But the uncertainty principle is not merely about clumsy instruments. It is a feature of quantum states themselves. A particle described by a very definite position has a more spread out range of possible momenta. A particle with a very definite momentum has a more spread out possible position. This is connected to the wave-like nature of quantum systems. Waves that are sharply localized require many wavelengths mixed together, and those wavelengths correspond to different momenta. The uncertainty is built into the structure of the description. Nature is not hiding a perfectly classical answer just beyond human reach in the usual way. The quantum state itself does not contain both exact values simultaneously. This leads naturally to the measurement problem. If a quantum system is described by a wave function containing multiple possible outcomes, why does a measurement produce one definite result? Why does a detector click here rather than there? Why does a screen show one mark instead of a soft blur of alternatives? Why does the world appear definite when its foundation is described by probabilities? Niels Bohr and the Copenhagen interpretation offered one influential way to think about this. In that view, quantum mechanics gives the probabilities for measurement outcomes, and measurement plays a special role in connecting quantum possibilities with classical results. Bohr emphasized that experimental arrangements matter, and that the language of classical outcomes remains necessary when describing what is observed. This approach helped generations of physicists use quantum mechanics effectively, even while deeper questions remained open. Hugh Everett later proposed a very different idea, now commonly associated with the many worlds interpretation. In this view, the wave function does not collapse into a single outcome. Instead, all possible outcomes occur in different branches of a larger reality. This is a bold and controversial interpretation, and it should not be treated as established fact. It is one way of trying to make sense of the mathematics without adding a special collapse process. Like many interpretations of quantum mechanics, it shows how difficult the measurement problem remains. The calculations work beautifully. The meaning beneath them is still debated. A crucial modern idea for understanding why reality looks classical is decoherence. Decoherence describes how quantum systems lose visible interference between alternatives when they interact with their environment. Dieter Zeh and Wojciech Zurek played important roles in developing and applying this idea. A tiny isolated quantum system can maintain delicate relationships between possible states. But ordinary objects are not isolated. They are constantly interacting with air molecules, photons, heat, surfaces, vibrations, and surrounding fields. These interactions spread quantum information into the environment, making superpositions effectively impossible to observe as simple alternatives at everyday scales. Decoherence does not necessarily solve every philosophical part of the measurement problem. It does not by itself tell every interpretation exactly why one particular outcome is experienced, but it explains why quantum possibilities become effectively classical in large, warm, messy systems. A dust grain in sunlight, a chair in a room, a human body, or a cup of tea is interacting with the environment far too much to behave like a delicate, isolated electron in a laboratory experiment. The wider world is constantly, quietly, and very efficiently entangling with everything in it. That is why reality looks definite, not because quantum physics disappears, but because quantum behavior becomes hidden inside enormous systems of interaction. The probabilities remain part of the deeper theory, but the large-scale world settles into stable patterns. A table does not appear in many visible positions at once because its quantum alternatives have decohered into effectively separate histories long before the eye could notice anything unusual. The world becomes classical not by abandoning quantum rules, but by being too large, too warm, and too entangled with its surroundings to display quantum delicacy openly. This is also why quantum physics does not mean reality is imaginary. It does not mean that the moon appears only when someone looks, or that thought casually creates matter, or that ordinary life is a dream held together by attention. Those are tempting exaggerations, but they are not the careful scientific picture. Quantum physics says that the deep rules of reality are not the same as everyday intuition. Measurement, probability, uncertainty, and environment all matter in ways classical physics did not expect. The familiar world is therefore both stranger and steadier than it seems. At its foundation, nature is described by wave functions, probabilities, uncertainty, and quantum interactions. At human scales, those same rules give rise to a world that feels definite enough to trust. The floor remains beneath the feet. The cup remains on the table. The shadow stays where light and matter place it. Reality looks settled because quantum possibilities, in the busy warmth of the everyday world, are constantly being woven into stable appearances. The surface is calm, the depths are probabilistic, and somehow, from that hidden uncertainty, the ordinary world becomes clear enough to live in. Some parts of quantum physics are strange because they make tiny things behave unlike ordinary objects. Electrons act like waves. Light arrives in photons. Particles tunnel through barriers. But quantum entanglement is strange in a deeper way, because it challenges the simple idea that the world is always best understood as separate pieces, each carrying its own independent properties. Entanglement happens when quantum systems share a combined state, so that the whole system has a clearer description than its individual parts. Two particles can be separated by distance, yet still belong to one shared quantum description. If one particle is measured, the result is connected with what can be found about the other, even when they are far apart. The important point is not that one particle sends a little message to the other. It is that quantum mechanics describes the pair as a linked system, where the relationship between the parts is fundamental. This idea disturbed Albert Einstein deeply. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published a famous argument now known as the Einstein-Podolsky-Rosen paradox. They were trying to show that quantum mechanics might be incomplete. Their concern was that quantum theory seemed to allow strong correlations between distant systems in a way that clashed with the older expectation of local realism. Local realism is the broad idea that objects have definite properties of their own, and that influences should not travel faster than light. Einstein did not like the thought that measuring one system could be connected so sharply with another distant system if no signal had time to pass between them. He famously objected to what he saw as spooky action at a distance. The phrase is memorable, though quantum physics has spent much of its time since then quietly insisting that spooky is not a technical term, however tempting it may be at certain hours of the evening. For a while this debate seemed partly philosophical. Quantum mechanics worked extremely well, but the deeper meaning of entanglement remained unsettled. Then John Bell changed the situation. In the 1960s, Bell developed a theorem showing that the disagreement could be tested experimentally. Bell's theorem provided a way to ask whether the correlations predicted by quantum mechanics could be explained by simple local hidden variables. Hidden variables would be unseen properties carried by particles, deciding measurement results in advance while preserving a more classical picture. Bell showed that if local hidden variable theories were correct, certain statistical limits should hold. Quantum mechanics predicted that those limits could be violated. This meant the question was no longer only about interpretation. Nature could be asked directly. Experiments followed. Stuart Friedman and John Clauser performed an important early Bell test experiment in the 1970s using entangled photons. Alain Aspect and his collaborators carried out highly influential experiments in the early 1980s, strengthening the evidence that quantum predictions were correct. More recent experiments have reduced major loopholes, and Anton Zeilinger's work with entangled photons helped develop entanglement from a philosophical puzzle into a practical resource for quantum information science. Clauser, Aspect, and Zeilinger later shared the Nobel Prize in Physics for experiments with entangled photons and their role in opening the field of quantum information. The results are clear in the broad scientific sense. Quantum entanglement is real, and the correlations it produces cannot be explained by simple local hidden variable models of the kind Bell tested. But this should be understood carefully. Entanglement does not allow faster-than-light messaging. It does not mean one person can affect another person's thoughts across the planet. It does not mean everything in the universe is magically connected in a way that can be used at will. It is precise, mathematical, limited, and experimentally measurable. The reason entanglement cannot be used to send messages faster than light is that each local measurement result still appears random. Only when the results from both sides are later compared, through ordinary communication, do the correlations become visible. The connection is real, but it cannot be controlled in the way a message would require. Quantum physics remains compatible with the rule from special relativity that usable information cannot travel faster than light. Entanglement now sits at the heart of quantum information science. Quantum information treats quantum states themselves as carriers of information, with properties such as superposition and entanglement becoming useful resources. In quantum cryptography, entanglement and related quantum principles can help reveal whether an eavesdropper has disturbed a communication system. In quantum computing, entanglement can help link qubits into states that have no simple classical equivalent, allowing certain kinds of calculation to be approached in new ways. Laboratory experiments now create and manipulate entanglement in many physical systems. Entangled photons can be sent through optical fibers or free space. Atoms and ions can be trapped, cooled, and controlled with lasers. Superconducting circuits can be engineered so that electrical states behave quantum mechanically. These systems are delicate, difficult, and often extremely cold or carefully isolated, but they show that entanglement is not merely an old argument from a textbook. It is a measurable feature of the world and a working tool of modern physics. So why is entanglement not obvious in everyday life? The answer returns to decoherence. Ordinary objects are constantly interacting with their surroundings. Air molecules, heat, light, vibrations, surfaces, and countless other environmental details rapidly spread and scramble delicate quantum relationships. Entanglement does not vanish from the universe, but it becomes dispersed into enormous numbers of degrees of freedom, making the clean entanglement of a small laboratory system impossible to observe in a simple everyday way. A cup of tea is not visibly entangled with a biscuit in a useful, controllable quantum sense. It may be emotionally connected depending on the evening, but physics must remain disciplined. Large, warm objects are too complex, too noisy, and too entangled with their environments to display the neat correlations seen in carefully prepared quantum experiments. The quantum links become buried inside the vast messiness of ordinary matter. Still, entanglement deepens the meaning of quantum physics shaping reality. It shows that the world is not always best described as a collection of separate little parts, each carrying complete independent properties. Sometimes the whole quantum state matters more than the pieces considered alone. Relationship is not merely something added after objects exist. In quantum mechanics, relationship can be part of the basic description. This does not make everyday reality unreal. It makes its foundations less separable than intuition expects. The ordinary world appears made of independent objects because decoherence, scale, and environmental interaction hide delicate quantum structure. But beneath that stable appearance, quantum theory reveals systems whose properties can be shared, correlated, and described only through the combined state. Entanglement is not a magical thread tying everything to everything else. It is stranger and more exact than that. It is the discovery that, at the deepest levels tested so far, nature sometimes writes its facts across more than one system at once. The world you know is built from parts, but quantum physics quietly reminds us that the parts are not always the whole story. The familiar world has a comforting way of hiding its own depth. A table does not look like a quantum object. A lamp does not seem to be performing a careful exchange of photons and electrons. A glass of water does not appear to be held together by molecular geometry, hydrogen bonding, and the strange allowed arrangements of quantum states. A phone feels like an ordinary object in the hand, smooth and solid, even though inside it, carefully engineered semiconductor materials are controlling the motion of electrons through structures so small that everyday imagination begins to lose its footing. And yet all of these things belong to the same hidden story. Quantum physics shapes everyday reality not from far away, but from underneath. It explains why atoms are stable, why electrons do not simply collapse into nuclei, why light comes in photons, why matter can form molecules, why chemical bonds have specific strengths and shapes, why materials can be hard, soft, transparent, colourful, magnetic, conductive, insulating, or flexible. It explains why a screen can glow, why a laser can form a precise beam, why a solar panel can turn light into electric current, why a medical scanner can use spin inside atomic nuclei to build images of the body, and why digital devices can process information through tiny switches built from quantum-controlled matter. The ordinary world is not quantum physics made dramatic. It is quantum physics made stable. A wooden table is held together by atoms arranged into molecules and fibers, with electrons occupying quantum states and bonds shaped by electromagnetic interactions. The table feels solid because electron clouds resist being pushed into the same arrangements, and because charged particles repel and organize themselves according to quantum rules. A phone depends on silicon, semiconductors, transistors, light-emitting diodes, photons, and controlled electron movement. A lamp glows because energy is being transferred into light and heat, with photons carrying energy away. A glass of water depends on the quantum structure of hydrogen and oxygen atoms, covalent bonds within each molecule, and hydrogen bonds between neighbouring molecules. A plant leaf looks green because chlorophyll absorbs some wavelengths of light more strongly than others, guided by the electron structure of its molecules. A magnet works because electron spin and electron arrangement create magnetic behaviour in matter. A human body lives through chemistry, metabolism, enzyme activity, nerve signalling, vision, breathing, and molecular machinery, all resting on quantum-shaped atoms and bonds. The strange thing is not that quantum physics exists somewhere beneath all this. The strange thing is that it becomes so ordinary. At the scale of atoms and particles, quantum systems can behave in ways that seem deeply unfamiliar. A wave function describes possible states. Energy can come in discrete amounts. Electrons can show wave-like behaviour. Particles can tunnel through barriers. Entangled systems can share a combined state that cannot be reduced neatly to separate parts. Measurement involves probabilities rather than simple, hidden classical facts. These ideas can feel distant from daily experience, almost as if they belong to another universe. But they do not belong to another universe. They belong to this one. The reason the everyday world does not look wildly quantum is not that quantum physics stops operating. It is that large objects contain enormous numbers of particles, constantly interacting with one another and with their surroundings. A single electron can be carefully isolated in a laboratory and allowed to show delicate quantum behavior. A table cannot. A table is warm, crowded, noisy, and deeply entangled with the air, the floor, stray photons, vibrations, and the rest of the environment. Its quantum alternatives do not remain clean and observable. Through decoherence, the delicate relationships between possible states become spread into the surroundings, and the world settles into appearances that behave classically for all practical purposes. Decoherence helps explain why a chair does not appear in many visible places at once, why a cup does not behave like an isolated particle, and why a human body does not drift through several obvious alternatives before breakfast. Large numbers of particles and constant environmental interaction make the world look definite, stable, and ordinary. The quantum rules are still there, but their weirdness is softened by scale. It is like hearing a single violin note compared with hearing an entire city at once. The individual details have not vanished, but the large-scale result becomes something very different. This is why common sense is not useless. Common sense works well at human scales because human beings evolved inside a world where quantum effects are usually averaged into classical behavior. It is perfectly reasonable to expect a stone to fall downward, a door to remain closed, and a mug to stay on the table unless someone knocks it off. Classical physics remains extraordinarily powerful for describing motion, forces, heat, light, and matter in many everyday situations. The mistake is not using common sense. The mistake is assuming common sense reaches all the way down. Quantum physics explains why common sense is an approximation. It shows why the world seems continuous, solid, and definite, even though, at deeper levels, it is built from quantized energy, wave functions, fields, probabilities, and particles that do not behave like tiny versions of familiar objects. The everyday world is not false, it is emergent. It is the large-scale pattern produced when countless quantum systems interact in stable ways. There are still open questions. The measurement problem remains one of the deepest puzzles in the foundations of quantum mechanics. Physicists continue to debate interpretations, including the Copenhagen interpretation, many-worlds interpretation, pilot wave theories, objective collapse models, and other approaches. Quantum gravity remains unfinished, because general relativity describes gravity and space-time beautifully at large scales, while quantum theory describes matter and forces beautifully at small scales. Yet combining them into one complete framework has proved extraordinarily difficult. The deeper relationship between quantum theory and space-time is still one of the great frontiers of modern physics. Those open questions matter. They show that quantum physics is not a finished bedtime story, with every page neatly tucked in. It is a working theory of astonishing success, surrounded by profound questions about what its mathematics means and how it fits into the deepest structure of the universe. Still, the central point remains calm and clear. Quantum physics is not merely strange behavior in laboratories. It is not only double-slit experiments, particle accelerators, or mysterious thought experiments involving cats who deserved a quieter afternoon. It is the working foundation beneath normal matter and modern technology. It is present in the chemistry of water, the glow of screens, the strength of materials, the warmth of sunlight, the colour of leaves, the magnet in a speaker, the silicon in a processor, and the molecules inside every living cell. The world you know is not less real because it is quantum. It is more delicately organised than it first appears. Reality is not a thin surface with nothing beneath it. It is a layered structure, where ordinary life rests on rules too small and subtle for the senses to notice directly. The table, the lamp, the glass of water, the phone, the plant, the magnet, and the body are all familiar forms of a deeper order. The surface is solid enough to trust, the foundation is strange enough to wonder at, and between them lies the quiet truth that everyday reality is not separate from quantum physics. It is what quantum physics becomes when the hidden rules of the small world gather into something large, stable, and beautifully familiar. So how does quantum physics shape the world, you know? It does so quietly, from beneath the surface. It shapes the world because it governs atoms, light, electrons, chemical bonds, materials, heat, magnetism, technology, and the stable structure of matter itself. It is not just a strange theory about particles in laboratories. It is part of the reason there are laboratories at all, along with walls, glass, lights, wires, screens, hands, eyes, oxygen, water, and the warm, ordinary world that seems so steady around you. The journey begins with classical physics, with Isaac Newton's laws of motion and gravity, and James Clerk Maxwell's great theory of electromagnetism. Those ideas still work beautifully across much of everyday life, but they could not explain everything. They struggled with blackbody radiation, atomic stability, the photoelectric effect, and the behaviour of light and matter at small scales. Max Planck's quanta showed that energy could be exchanged in discrete packets. Albert Einstein's photons revealed that light could behave as individual units of energy. Matter waves showed that electrons and other particles were not simply tiny classical objects moving along neat paths. From there, the hidden architecture became clearer. Atoms do not collapse because electrons occupy quantum states rather than classical orbits. The Pauli exclusion principle helps give atoms their layered structure and contributes to the solidity of matter. Quantum chemistry explains why atoms bond, why carbon is so versatile, why water has its shape, why DNA can hold information, why proteins fold, and why medicines can interact with the body. The strength, texture, colour, flexibility, and conductivity of materials all depend on atomic structure, electron arrangement, crystal structure, and quantum bonding. Modern technology rests on the same foundations. Semiconductors work because of quantum band structure. Transistors control electron behaviour inside engineered materials. Lasers depend on stimulated emission. Screens glow because electrons and holes recombine and release photons. Quantum tunneling helps explain processes inside stars and inside certain electronic devices. Spin gives rise to magnetic behaviour and makes magnetic resonance imaging possible. Superconductors and superfluids show that, under special conditions, quantum behaviour can rise into view at a visible scale. Even biology, from photosynthesis to enzyme activity to vision, rests on molecules whose chemistry is shaped by quantum rules. And deeper still, quantum field theory describes particles not as tiny beads in empty space, but as excitations of underlying fields. Quantum electrodynamics explains the interaction between light and charged particles with extraordinary precision. Probability, measurement, uncertainty, decoherence, and entanglement reveal that the foundations of reality do not behave like the simple, definite world of everyday intuition. And yet, everyday reality remains real. A table is solid enough to lean on. A glass of water is still wet. A lamp still shines. A plant leaf still gathers sunlight. A human body is still warm, living, and meaningful. Quantum physics does not make the familiar world imaginary. It explains why the familiar world has reliable form, colour, texture, chemistry, warmth, and technological possibility. The evidence is not vague or decorative. It appears in black-body radiation, the photoelectric effect, electron diffraction, atomic spectra, semiconductor technology, lasers, magnetic resonance imaging, and precision tests of quantum electrodynamics. These are not just philosophical curiosities. They are measurements, machines, observations, and working technologies. There are still open frontiers. The measurement problem remains deeply debated. Interpretations of quantum mechanics continue to ask what the mathematics really means. Quantum gravity remains unfinished. The relationship between quantum theory and space-time is still one of the greatest unresolved questions in physics. And the deepest reason the quantum world gives rise to the classical world people experience remains a place where knowledge is strong but not complete. Still, the central truth is calm enough to hold. The world does not become less familiar when its quantum foundations are understood. It becomes quietly more remarkable. The ordinary surface remains, the table, the light, the water, the body, the leaf, the screen, the room. But beneath it all is a hidden depth, precise and strange, holding matter together and allowing reality to take shape. Everyday life has been carrying quantum physics all along.